Hello. This will be the first in a lecture series on college algebra. Today we're going to look at the first chapter in the OpenStax college algebra book. I'm going to be using the OpenStax book as a kind of guide, but I won't be following it necessarily religiously. I just like to have a text as a resource. So if you wanted to do some exercises from these sections, you can do so. I will put the links to the OpenStack and the OpenStack College Algebra book in the description, which you can find and read through. Today we'll call this lecture 1, and we're going to talk about the real numbers, which we will construct from sets of other numbering systems, not quite systems, but numbers of sets. The first one we will call the natural numbers. The natural numbers are the numbers 1, 2, 3, 4, 5, etc. These three dots will mean continues. And if there's nothing on the other side of this dot, 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 that means it goes on forever. Now, set notation, we use these squiggly lines to denote a set. In other words, we will have a set, say, that has the elements A, B, and C. The squiggly lines will let us know that what we have is a set. My squiggly lines are not great, so bear with me. I think in context, you'll understand. So because the natural numbers are used often, we have a special notation for them. We call it this fancy n. The fancy n equals the set, again, 1, 2, 3, etc. forever. Now, the book uses the notion of a whole number set, and the whole numbers are just the natural numbers, and we're going to have a fancy W. I don't like that. Let's do it like this. And it's basically just the natural numbers with 0. The book does it. I might have made the caveat, the natural numbers, and added 0 to it. Some professors do that. Others leave it as is. But this is how we'll do it. So we have the natural numbers and the whole numbers. Another important set is something we call the integers. integers. And the integers are the natural numbers and 0, or the whole numbers, and the negative of each. So in other words, we will write it like this because we want to denote that it's infinite in either direction. So we'll start at some point and we'll go on forever. You can write out many more terms if you want to. In other words, my starting at -2, -1, 0 is just a choice. You don't have to do it that way. You could start -100 and count down from 100 to 0, but I like to keep it short. So that is the set of integers. And notice we have positive integers, which of course are 1, 2, 3. Negative integers, which would be -3, -2, -1, and of course 0, which is just a set that has 0 in it. So positive integers are basically the natural numbers as we defined it, with 0, which is the whole numbers, and then the negative of the positive integers. And we have a special notation for the integers as well, because we use the notion of the integer a ton. So it's a fancy z, and the fancy z again will be the set that has all of the counting numbers 0 and their negative. Now, why z? Why not I? We have w is whole, n is natural, z is integers. It's a German word, Zahlen, which means numbers. So somewhere along the mathematical continuum, somebody decided that the integers were going to be called Zahlen, Z, and that's the notation we use. All right, so now we have the natural numbers, whole numbers, the integers, and an important concept, again, another numbering set. So we'll call these the rational numbers. And the rational numbers, we have to be a little more fine with it. And so we define the rational numbers as the set of a fraction a over b such that a is an integer, b is an integer, and b is not equal to 0. So a couple notes just to be consistent here. We have the set notation, and then we have this little vertical line. This means such that. So when we read the set, it says the set that contains a over b such that, and then we have a definition of a as an integer, b as an integer, and b is non-zero. A better way to write this, of course, would be to shorten the a, b as an integer. And to do that, we need another notation, which looks a little like an e, and which means element of, or sometimes just in. So if I want to say that a is in a set, I do this. And since we have the integers, remember fancy z is the integers. So this means a is in the integers. And it's just a more concise way to write this definition. So a over b, where a and b are integers and b is non-zero, meaning b could be anything but 0. Okay, so that's how we have the rationals defined. And this also has a special notation, the fancy Q, which again is a and b in the integers, where b is non-zero. Now notice we're not listing them like we did with the naturals, wholes, or integers. It's sufficient to write it this way, but we could write out a bunch of rational numbers, but this is a little bit difficult. We can do, say, 1 over 2, 1 over 3, 1 over 4, but we have to include 2 over 2, 3 over 2, 4 over 2. So the ordering can be a little tricky. So we just write the definition this way. Now the Q comes from just the word quotient, which is a fraction. Okay, so a little bit of explanation of what this means. So if I have 15/4, 15/4 is a fraction. In fact, 15/4 is 3.75. And we say 15/4 is a rational number. It's in Q. Notice that I can write it as a decimal. Now, what's important about this decimal is we say this decimal terminates. It stops. It's 3.75, that's it. And let's look at something a little more tricky. 4/11 is 0.363636, and so on. It doesn't stop. It's always 3636. We write this when it repeats. We put a line over the parts that repeat. So 3 and 6 repeat. So 363636. Notice this does not terminate. So it does not terminate. But repeats. This is important because when we define what's an irrational number, we're going to use a little bit of this terminology. So we have what's called rational numbers. Now we have what's something called irrational numbers. Now, irrational numbers have a particularly unsatisfying definition as being not rational. And remember, the definition of rational means we can express as a fraction where a and b are integers and b is non-zero. So we can think of irrational numbers as not expressible as a fraction of integers. That part's important, the integers part. Meaning if I have, say, the square root of 2, some of you might have already noticed that I can write the square root of 2 as a fraction, the square root of 2 over 1. But the square root of 2 is not an integer. So I cannot express the square root of 2 this way and say it's rational. The square root of 2, I would need it to equal a and b, where a and b are integers and b is non-zero. If I can do that, then the square root of 2 is rational, but we cannot express it that way. Now, another fact, the square root of 2, let's say, as an example, is square root of 2 is 1.4, approximately, 142 ... This does not terminate and does not repeat. So we can also think of irrational numbers as non-repeating, non-terminating decimals. And this is convenient as well, though it's impossible to say that something doesn't repeat that's infinite, because we can never know exactly every single digit. There are people that have looked at pi, for example, to many digits, and they have yet to find a repeating pattern in pi. So pi is a non-repeating, non-terminating decimal, and so pi is irrational, like the square root of 2. So those are common examples of irrational numbers. You can think of many more. There are infinitely many of them, just like there are infinitely many rational numbers. This gets a little bit into set operations that we don't want to get into here, but sometimes we express the set of irrationals as the real numbers without the rational numbers. Now, why would this be true? Well, if I'm given any number, the number is either rational or irrational. And the caveat is never both. It can never be both rational and irrational. So given every number, it's either rational or irrational. So the real numbers without the rationals, meaning I take the reals and throw out all the rational numbers, I'm left with the irrationals. So sometimes we express it that way. So now what we have is the real numbers when we combine all of these lovely sets of numbers. So when we combine the rationals and irrationals, we get the set of reals. Reals are constructible on a number line. So let's say we have a number line. I'm going to plot out just some markers here. I'll do the integers. So the real numbers are every point on this line, including the integers, including the whole numbers, including the natural numbers. So for instance, I can plot the square root of 2, which we said is about 1.4. So that guy would be here. We know that pi is 3.14, etc. That would be approximately here. Conversely, we would have negative pi would be somewhere over here. And then the negative square root of 2 would be somewhere here. So every point on this number line, it corresponds to a real number. And these go on into the infinite and negative infinite direction. So we can pull any point, and that'll represent some real number. All right, so why do we need all of these designations? Well, partly because it's convenient when we're talking about particular numbers, solutions to equations. If we talk about set operations, we have numbers of integers combined with numbers of irrational numbers, so on. But notice something, we can express these number systems. I don't know if systems is a great word. It's called number sets as a picture. Some of you are probably familiar with the Venn diagrams, where if I have a set here, a set here, the intersection of these two sets is the colored in spot. So that means that they intersect. So these numbers will correspond in this way. So let's say this guy is the natural numbers. Now the whole numbers are the natural numbers with 0. So I'll just not write that for now. Let's just have the natural numbers. I don't love that either. There. In the integers, our lovely z is this set, and you can see inside the integers we are contained with the natural numbers, and then inside that we have the rational numbers, and of course encompassing all of these are the real. So if I use the concept of containment, we won't get too deep into this. This means subset. It's a way to denote what we've just drawn. So the natural numbers are a subset of the integers, are a subset of the rational numbers, are a subset of the real numbers. So what does that mean? Well, the first thing is we want to think about how can we classify numbers. And a number can be in more than one set. So for instance, example, 1/2. What kind of number is 1/2? Well, we know it's a real number because all numbers are real numbers. Any number you can think of is a real number. So 1/2 is rational because I can express it as a fraction of integers. 1 is an integer, 2 is an integer. It's not an integer because it's a fraction, and it's a real number. So you can see I can define 1/2 as a rational number and a real number. How about 2? How can we define 2? Well, we know that 2 is a natural number just by our set above. And we know that any natural number is also an integer. So 2 is a natural number and it's an integer. Now it's a rational number. Now, how is it a rational number? Well, because I can express 2 as 2 over 1. 2 is an integer, 1 is an integer, 1 is not 0, so it's also rational. So everything's real, so it's a real. So 2 is natural, integer, rational, and real. In other words, if we look, 2 exists in this, which means it exists in here, and exists in here, and exists in here. How about the square root of 3? Well, 3 is prime, so I know I can't break up 3 other than 3 times 1. I also know that if I were to write this decimal expansion, it would be non-repeating, non-terminating. You can put it in your calculator, and your calculator will terminate it just because it's impossible to list an infinite list of numbers. So this is irrational and real. Now, why isn't my irrationals part of this? Well, it just, the irrationals are a subset of the real numbers, but the naturals, integers, and rationals aren't subsets of the irrational. So the only relationship between the irrationals and the reals is this. It doesn't fit nicely in that set containment. So we just sort of think of that differently. All right, so let's look at some examples, and this will be classification. We just want to see if I give numbers, where are they, or what are they? So an example would be, let's identify these. Identify as, let's say, rational, irrational, whole, and natural. So that's it. We want to identify them as one of these. So we have A, B, C, and D. Let's do square root of 2, 37, 11 twelfths, and 0. All right, so we just have to identify these based upon our definitions above. Square root of 2, I think we've talked about. This is irrational. I know it's real, but we only want to classify them in as real, or sorry, rational, irrational, whole, or natural. Now, 37 is a whole number, and it's a natural number. The more you do these and think about it, the whole natural is going to dissolve into just basically the naturals with 0. But for now, let's keep them separate. 11 halves, this is a fraction. 11's an integer, 12's an integer, so we say this is rational. Now 0, we can express 0 as a fraction, but that's not really one of our choices. So we'll say 0 is a whole number because we're not including 0 in our naturals. But one aside, I said 0 was a rational number because anything divided by 0 is, or any number that divides into 0 is 0. So I can really take any integer and express 0 as a fraction. So technically 0 is a rational number. It can be expressed as a fraction of integers. All right, so let's do a little bit of our set notation. So let's say classify as natural, integer, rational. I'm going to use this as a symbol of irrational. Your book does, or the book does this. I don't love that either, but we'll just use the reals without the rationals. So we have A, B, C, D. Let's look at the square root of 49. Say 8/3. Then I have 1, 2, 1, 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2. Repeating that pattern. and the square root of 19. All right, so we want to classify these as natural, integers, rational, irrational, and real. So let's take these one by one. The square root of 49 can be evaluated. That's 7. Well, that's an integer, a natural number, a rational number, and a real number. Technically, it's a whole number too, but that wasn't one of our choices. So B is 8/3. 8/3 is 2.666 forever, which we can write, again, we put the little line on top of it to denote that this part repeats forever. But we can see we can express it as a integer divided by an integer or a fraction. And so this is rational and, of course, real. Now, what about 3.12122122221222221, so on? Is this rational? Is this irrational? Is it real? Well, of course it's real. It's not natural. It's not an integer. The question really is this a rational number or irrational number? Well, this goes on forever by the ... And if you can sense that what's happening is I'm adding one more 2 between the ones. This doesn't repeat. As much as it looks like there's a pattern, it does not repeat. Because it doesn't repeat or doesn't terminate means that it is irrational. This will never be expressible as a fraction. It's a non-repeating, non-terminating decimal. And finally, square root of 19. Again, 19 is prime. So this cannot be expressed as a fraction. It will be a non-repeating, non-terminating decimal. So this is also an irrational number. All right. So that ends the look at the real numbers. Hopefully this made sense. Again, you could try some of the exercises in the book. A lot of it's just classification of numbers, similar to the examples we did here. So that's it for lecture 1. Stay tuned for lectures 2 and so on. I think the next set will be order of operations. The next set of lectures will be order of operations and still in the prerequisite preliminary stages. So look out for that. Please like and subscribe, and I appreciate you watching. Good afternoon. We are continuing with our college algebra lectures. This is lecture 2. We are using as a guide the OpenStax College Algebra 2nd edition. We are in chapter 1, section 1.1, if you're following along with that. If not, otherwise, we are doing today the order of operations, PEMDAS, the properties of real numbers, which includes the commutative properties, the Schulze properties, the distributive property, and then the additive multiplicative identities, additive and multiplicative inverses. And then we'll look at algebraic expressions and simplifying algebraic expressions. Seems like a lot, but it should go rather quickly, I think. So let's start with the order of operations. And this should all act as a review before we get into the actual meat of the college algebra lectures. So this mnemonic that most of you have probably heard, the PEMDAS. In the PEMDAS, we have the parentheses. We can also think of them as brackets. They will be like that. Exponents. Multiplication and division. And addition of subtraction. So this is the order in which we do arithmetic. All right, so quickly, before we start, let's look at a quick exponential. So an exponent, we have a base b and an exponent x. B is the base, and we say what it's raised to, we say it's the power. Right, so 2 squared, the base is 2, the power is 2, and this relates to multiplication in this fashion. We multiply the base however many times of the power. So 2, we multiply 2 times. So we have 4. Another example is x to the 4th. That means we multiply x 4 times. We will go over exponents, I think, in lecture 3, a little more in detail, but for now, this should be sufficient. All right, so the order of operations, I'm going to assume that you know arithmetic. I'm going to assume that you know addition, subtraction, multiplication, and division. So when we look at examples, I'm not going to explain that arithmetic. So let's just look at the order of operations really quick in an example. Again, this is sort of the preliminary chapter of a college algebra textbook where we get familiar or refamiliarize ourselves with some of the things prior to a college algebra course. Some courses might skip these things. And if you're looking at these lectures, you could probably skip to, I'm guessing, chapter 2, which will be the core of the beginning of the core of the college algebra course. So, but if you need these preliminary refreshers, these are good. That's why I'm doing these. So, example, let's write 25 plus 7 times 3/4 minus 6 squared. So we're applying PEMDAS. And the mnemonic, obviously, parentheses, exponents, multiplication, division, addition, subtraction. So we notice there are no parentheses here. So we don't have to worry about the parentheses. Exponents. I see there's a 6 squared. So we will begin by squaring 6. And we keep the sign out front. So negative 36. There's something to note. I see this commonly with students. 6 squared, negative 6 squared is negative 36. However, negative 6 quantity squared is equal to 36. The reason is this is really just negative 6 times 6, whereas the second one is negative 6 times negative 6. We know that negative times a negative is a positive, so we get 36. And this is 36, and we hold on to the negative. So that's why the 6 squared is negative. If it was quantity 6 squared, negative 6, then it would be positive 36. All right, so that's the exponents. Now we look at the multiplication, and we do the multiplication and division left to right. So whatever comes first, moving left to right. So the first thing we see is we have 7 times 3/4. So we can think of this as 7 over 1 times 3 over 4. We multiply the top, and when we multiply the bottom. So then we get 21/4. So let's put that in line here. So I should write equal signs. So 25 plus 21/4 minus 36. Now we look for any more division or multiplication. We don't see any. So now we do addition and subtraction left to right. So the first thing we're going to look at is the 25 plus 21/4. So we need a common denominator, add fractions. So I'm going to write 21/4 over here. And to get a common denominator, we essentially have 25 over 1. So if I multiply the top and the bottom, I'm going to get 100 over 4 plus 21 fourths. This again allow us to have a common denominator of 4, and then all we need to do is add the top of the fraction. So 100 plus 21 is 121. So 25 plus 21 fourths is 121 fourths. So let's write that 121 fourths minus 36. Now you guessed it, we're going to find a common denominator between 121 fourths and 36, which means we're going to take 36 over 1 and multiply it by 4 over 4. That gives us 121 minus 144. And then we have a common denominator of 4. And 121 minus 144 is negative 23rd fourths. So with the order operations, what we get is negative 23rd fourths. Let's do another example real quick, a little more complex. The square root of 5 squared minus 4 squared plus 19 times 7 minus 6 quantity squared. PEMDAS, so we're going to look for parentheses first. So we see we have a parentheses here. So I'm just going to subtract 7 and 6, which leaves us with 1 squared. Now we have an exponent. We have this squared. This technically is an exponent. We'll get to that in the exponent section, but the square root is a rational exponent. But let's think of this too maybe as a quantity. It's underneath the square root. So we have 25, that's 5 squared, minus 16. 1 squared is just 1. Now let's evaluate the square root. 25 minus 16 is 9. Now we could evaluate the square root. The square root of 9 is 3. 19 times 1 is 19. So that was the multiplication division. So we did the exponents, multiplication, division. Now we're going to add. So that is 22. All right, simple enough. Order of operations. PEMDAS is always a good way to think about that. This will always be true in algebra. There'll be cases and logarithms where we might expand or contract. We might look at the order of operations again a little more closely, but that's a ways away. All right, so now we're going to look at what's called the properties of the real numbers. In lecture 1, we looked at the real numbers and we built them up by looking at whole numbers, natural numbers, integers, rational numbers, irrational numbers. Here we're going to look at some of the properties of these. The first one, and again, this should all be somewhat review. We'll call this a commutative property of addition. So this is something that the real numbers have. And what we mean by that is that I can add, I'm using variables here, in any order. X plus y is the same as y plus x. A simple example of this would be if I take 4 plus negative 6, is that going to be equal to negative 6 plus 4? I'm just rearranging the order in which we're adding. So this is negative 2, and this is also negative 2. So we see that addition is commutative. Commutative, this means that we can add in any order. So we have also a commutative property of multiplication. And use variables, let's say x times y, it will be the same as y times x, meaning the order in which we multiply things shouldn't matter. Now, if you move on from college algebra to, say, linear algebra, you'll notice that if we multiply matrices, that it's non-commutative in some cases. So assuming that something is commutative is a mistake. Let's look at an example. 2 times -6, is that the same as -6 times 2? Well, we get -12 equals -12. So yes. So again, this is commutative, addition and multiplication. Now we're going to have association, or the associative property. And we're also going to have addition and multiplication. And this, let's use different variables, a plus b plus c. Now, if I group them this way, will this be the same as if I group them this way? So the associated property says that we can do that. And from your order of operations, we know that in the left-hand side, we would do a plus b first, and the right-hand side, we would do b plus c first. So let's see if that's actually true. So an example, let's say 2 plus 3 quantity plus 4, is that the same as 2 plus 3 plus 4? Now remember PEMDAS. So we're going to add 3 and 5, or 3 and 2, which is 5, plus 4. And then we're going to add 3 and 4, which is 7. 5 plus 4 is 9. 2 plus 7 is 9. So yes, these are the same. Even though the steps look like we're coming to a different conclusion, the real numbers are associative under addition. And I'm using really good examples. And so far I'm just using integers so as not to overly complicate. And the real numbers are also associative under multiplication. So let's say we have x times y times z. Not a question mark. This is a statement. This is true, that it's the same as x times y times z. So this is a fact. We can associate multiplication however we want in the real numbers. So an example, simple one, is 2 times 3 times 8. Is that the same as 2 times 3 times 8? Order of operations, we do parentheses first. 2 times 3 is 6 times 8. This is 24. 6 times 8 is 48. 2 times 4 is 48. So yes. So no surprise, that checks out. Those are pretty clean, quick examples. Now let's look at something that we use a lot in solving equations and in simplifying expressions, called the distributive property. And the distributive property says that if I have a number, a real number x, and I multiply it by the quantity of some sum, this will be equal to x times a plus x times b, meaning we distribute x through the addition. So an example, again, we're doing essentially this. We're multiplying x times a, and then multiplying x times b, and then we're adding those two. That's how we get the right-hand side. So let's use another simple example. Let's say 2, 5 plus 7. Is that the same as 2 times 5 plus 2 times 7? That is 12 times 2. This is 10 plus 14. So 24 is indeed 24. So you can see this distribution works fine. These are simple cases. As we get through the course, we will have a little more tricky things distributive-wise. Remember, FOIL is a form of distribution if you've done FOILing before. If you multiplied along polynomials, you've done another form of distribution. I want to talk about a special case before we move on. So notice that x minus y is the same as x plus negative y as a fact. So let's look at something like x minus 5 plus 3. Now, the order of operation says we do the parentheses first. We can add 5 and 3, which is 8, and then take 12 minus 8 will give us an answer. We could also think of this using the distributive property, and we can say, well, what we have, this negative is the same as negative 1. And so 12 plus negative 1 times 5 plus 3. And why are we doing this? It's sort of convenient because now I'm going to distribute negative 1 via our rule. What I mean is convenient is if we have a quantity of variables and a number outside, we can distribute. If there is no number and it's a subtraction, then we can distribute that subtraction, so to speak, in the form of negative 1. And then I get negative 5 minus 3, and that is minus 8. So now we have 4. So the distribution property with a subtraction of a quantity can be the same as distributing that negative, that subtraction through the quantity, which in simplifying or condensing things will be a little bit more straightforward and interesting once we get to that part. All right, so now we are going to talk about a couple identities. And again, these should be familiar. These are sort of a more rigorous way to think about things you already know. So identities, this is, let's say this is a definition. So we have something called the additive identity. We define this as there is some unique real number, which we're going to call 0, such that for any real number x, x times 0 is equal to 0. So it's a fancy way to say that we have an identity element called 0. Oh, I'm adding. I'm not multiplying. We have an identity element 0 for when I add 0 to anything, I get that number back. Meaning 2 plus 0 is 2, 3 plus 0 is 3, and so on. The additive identity meaning I get back what I started with. Now we have a multiplicative identity. And we can think of this as a definition as well. This will be, again, a unique real number called 1, such that for all x, for all real numbers x, x times 1 is equal to x. Unique meaning there's only one of these. There isn't two multiplicative identities. There isn't two additive identities. The only ones that are additive and multiplicative identities are 0 and 1. So again, 2 times 1 is equal to 2. 3 times 1 is equal to 3. The identity part means that we apply this in multiplication of 1, we get back the original number. That's what we kind of mean by identities. Okay. We're going quick, but I think most of you should have seen this at some point. So let's look at additive inverses. This should be another definition. I'm not spelling too well. So additive inverses, which means by definition for every single one, every single real number, we'll say x, every single real number x, there is a unique real number, which will be denoted by, I should say denote, denoted by 1 over x, reciprocal, right? These are called reciprocals. Oh, I'm doing the multiplicative, so let me just change this. This is a multiplicative identity. Inverse, my thought. Such that 1 times 1 over x is equal to 1. That is the multiplicative inverse. So every real number with one caveat, that x is non-zero. So 0 does not have a multiplicative inverse in that sense by this definition. So every non-zero x. So 2 times 1 over 2 is 1. 3 times 1 over 3 is 1. Square root of 2 times the square root of 1 over square root of 2 is 1. So no matter what real number you give me, I have the reciprocal and the additive inverse. Now, you might think, well, what if I have 1/3? What's the reciprocal of 1/3? Technically, it's 1 over 3, which is the same as 1/3 times 3, which is 1. Everything has a reciprocal except 0. So the next is what I wrote out but didn't complete. It's additive inverse. So again, for every real number x, there is a unique real number and we're going to call this negative x, such that x plus negative x is equal to 0. These are additive inverses. And in the case of additive inverses, what we get is the additive identity. In the multiplicative inverses, we get the multiplicative identity in 1 and 0. So yeah, anything times anything plus itself plus its inverse. So 2 plus -2, obviously it's 0. Square root of 2 plus its negative is 0. So these always exist. The reason we include 0 is it's sort of redundant, but -0 is 0. 0 plus 0 is 0. So technically 0 has additive inverse. So those are the properties of real numbers that we will use throughout the course, throughout every college algebra course. Now let's look at something called algebraic expressions. Algebraic expressions are a collections of numbers, variables, operations, such that there isn't an equal sign. An expression, let's give us some examples. X squared plus 2x is an expression. The square root of 3x to the fourth, y to the third is an expression. X to the third plus 4 is an expression. If I put an equal sign, that's an equation. So expressions lack the equal sign. So the couple things we need is we have x's and y's in here. So we call these variables. X and y are variables. And the constants here, it might not seem obvious that this exists here, but 1's a constant, 2, 3, and 4 are constants in these three expressions. The reason that 1 is here is because we always think of 1 existing in front of a variable if there isn't anything in front of the variable. So the coefficient of just x to the third is 1. For instance, 2x squared, the coefficient is 2. That's another expression. So in the book we're using as a guide, there are some problems in this section that ask you to look at expressions and classify some of the elements in there. So you can give that a shot and see if it makes sense. Let's evaluate some expressions. So we're going to take some random expressions. So example, x squared plus 2x plus 1. So it's an expression. There's no equality. X is variable. 2 and 1 are constant. So, but we can find the value of this if we're given some value for x. So let's say, suppose x is equal to 0. Well, I'm going to replace x in this expression with 0 and then perform the order of operations. Exponents, parentheses. You don't have to do these in steps. You can do them at the same time as long as you don't violate the order of operations. So I'm squaring 0. I'm multiplying 2 and 0. So that means that this expression is equal to 1 when x is 0. We can also pick another number. Again, I'm picking really nice numbers. You can challenge yourself if you want by picking something a little more ugly. So this would be 2 squared plus 2 times 2 plus 1. 4 plus 4 is equal, nope, plus 1. I don't know why I wanted to get rid of 1. It's equal to 8. I'm doing left to right, order of operations, 9. So when we evaluate this expression, when x is 2, the expression is equal to 9. Not too bad. Here's something you could try. Try x equals the square root of 2. Put the square root of 2 in there and see what you get. Okay. Let's try one more. Just a different look. So example, y plus 4 divided by y, let's say y squared plus 1. So this is an expression, there's no equal sign. So suppose that y again is 1. Well, I'm just going to replace in the expression y with 1. Now I'm going to do the top. 4 plus 1 is 5. The bottom, I'm going to do the exponent first. 1 squared is 1 plus 1. So we get 5 halves. Again, you can challenge yourself, pick a different number, pick something ugly. You could pick something like y equals pi divided by the square root of 3. Chug that in there and see what happens. Probably won't simplify very much, but you'll get a number. This will be a number. These aren't variables. Pi over square root of 3 is not variable. So you'll get something. So it leads us to the last topic for this video, simplifying algebraic expressions. So we're going to use the properties of the real numbers that we went through earlier, of course, arithmetic, to simplify some expressions. And expressions, again, are short little mathematical statements without equality. So let's look at an example. Here's an expression, 9 times x plus 8 minus 27. So we want to simplify this. We could just plug in values of x if we wanted to and find what the value would be. Or in this case, we can simplify it first, and then we have something that maybe looks a little bit better. And it's a little bit easier for us to manipulate once we're given values of x. So I'm going to use the distributive property first. That says that if I have the number out here times some quantity, I distribute the 9 to each term. So that's 9. I'm going to use parentheses to denote multiplication. 9 times x plus 9 times 8. And I'm going to leave this minus 27 out here. So left to right, I'm going to do the multiplication first. So we get 9x. And then we get 9 times 8 is 72 minus 27. So notice that 9x and 9x, the only difference here is I remove the parentheses. It's a lot easier to read this way. So 9x plus 72 minus 27. So then we get 9x plus 45. So we didn't evaluate, we just simplified. We just made the expression look better. And if you see, like these two things are the same, but one is simplified. One seems a little bit more straightforward if I want to plug in values for x. It's simpler on the left than on the right. Let's try something a little bit more complex. Again, I'm just going to use integers. So we have 9x plus 4x times 2 plus 3 minus 4 times 2x plus 3x. So to simplify, here we can distribute, we can do order of operations. We notice the parentheses, again, pemdas. We have like terms in the pemdas, in the parentheses, because 2 and 3 are the same kind of term. 2x and 3x are the same kind of term, so we can add those. So I'm going to add those. That'll be 5 minus 4. 2x plus 3x is 5x. Now, order of operations says we do multiplication left to right. Nothing we can do for 9x, but we can multiply these guys. So 4x times 5 is 20x. I'm going to assume you know how to multiply, again, variables with constants. If you should need that assistance, tell me in the comments, and I can do a short video on how to multiply with variables and add variables in like terms, but hopefully that makes sense to you. 4 times 5x is 20x. So we see that the 20x minus 20x just gives us 9x. So this long, ugly expression is really just 9x. That those two terms on the right there drop. And of course, if we replace x with some number, the bottom highlighted version is much easier than the top one. If we want to evaluate these expressions for any value of x. Again, try this. Put in x is equal to the square root of 2 over 3 and see which one is easier to do. Obviously, the bottom is going to be the easiest. if you're curious of what that would be, it's 9 times the square root of 2 over 3, which is equal to 9 square root of 2 over 3. And 9 divided by 3 is 3, so this is 3 square root of 2. Simple. All right, so that ends this lecture. I'll write end. Next time, lecture 3, we're going to dig into exponents. More detail, some of the exponent properties, how to manipulate exponents, how to add, subtract, all that great stuff. So look out for that. Thank you for watching. Like and subscribe if you can. It helps us out. Have a great night. Good afternoon. We are continuing with our college algebra lectures. This is lecture 3. We're still in the review or prerequisite section, which comes before the heart of the college algebra course or most courses. So this should be review if you took an intermediate algebra class or high school algebra. A lot of the stuff will be review. Lecture 3 will just be about exponents. So we'll go over product, quotient, power, zero exponents, negative exponents, power products and quotients, and simplifying expressions that have exponents in them. So this lecture will have a lot of examples. And we'll start here with the product. We'll call it the product rule, just to be consistent with the text. The product rule says if I have 2 of the same bases raised to some power, that I can add the exponents. So here, a is a base, and m and n are the exponents. Or simply powers. The power of a is m, the power of a is n. So when the base is the same, we could add them, but they must be the same. You can't add exponents of different bases. Here's an example. We have 2 to the 4th times 2 to the 6th. This is 2 to the 4 plus 6 and 2 to the 10th. Equivalently, we can have variables. So x squared times x to the 4th times x to the 6th will be 2 plus 4 plus 6, which would be x to the 12th. So same bases, we can add the powers when the bases are being multiplied. That's why we call it the product rule. Let's go on to the quotient rule. So the quotient rule is the case when we have 2 bases, the same bases, that are being divided, or we have a quotient. In this case, we subtract the exponents. So a to the m divided by a to the n is equal to a to the m minus n. Some examples: x to the 5th divided by x squared is equal to x5 minus 2 is equal to x to the 3rd. It's a way of simplifying, but also we can have something a little more complex. And we'll see later in this lecture that there are other ways to simplify something like this. But for now, we're just interested in the quotient rule application. So this would be x times the square root of 2. 5 minus 1 is equal to x square root of 2 to the 4. Now, a question you might have is, where did I get that 1? Well, if there is no exponent, we assume 1. So in this case, this is really to the 1, because anything to the 1 is itself. 2 to the 1 is 2. The square root of 2 to the 1 is the square root of 2. So we assume without notation that there is an existing a 1. And we'll see a little bit later how to further reduce something like this. But for now, we're just looking at the quotient rule. Let's look at what we're going to call the power rule. So if I have a to the m, and then the quantity to the n, this will be the same as multiplying m and n. So you should see this is not the product rule. This is not a to the m times a to the n, which we add m and n. This is a to the m to the nth. So let's look at an example. So x to the 4th squared. Now the rule just simply says that if this is the case, that I multiply these and I get x to the 8th. But why? Why is this the case? Well, let's remember what a power does. A power says that I'm going to take something. If I raise it to the power of 2, I'm going to multiply whatever it is by itself that many times. So in actuality, what we're doing is multiplying x to the 4th to itself twice. And this multiplication means we're doing the product rule. So we're adding the exponents. And so this is 8 to the x. You can see the top part of the example is quicker. We multiply 2 and 4. The bottom part is legitimate. It just has that little extra step in there. But it's the same. It's equivalently the exact same. So the power rule is nice. Let's do something a little more complex looking. And again, we can look at other ways to handle this simplification later. But the rule says I take whatever in the inside, the power, and I multiply it to whatever the outside power is. So this is 8 times 2. So that's 3y to the 16th. And again, we'll look in a little bit how to further reduce this or simplify or expand, however you want to look at it. So that's the power rule, the quotient rule, and the product rule. We're moving along. So let's look at what happens when we get 0 exponents. The rule is for any real number a, if I raise a to 0, it's equal to 1 for any real number a. And this is handy when we have a situation like this. We'll apply the quotient rule, which we just learned. It's 4 minus 4, and that's x to the 0, which is 1. Now, it should be obvious from the left that something divided by itself is always 1. In other words, 2 divided by 2 is 1. X to the 4th divided by x to the 4th is 1. But here's a more interesting reason why that's true in this case, because we'll have an exponent to 0. Let's look at something that's going to result in a 0 exponent, but is a little bit more complex looking. So you have x squared, x to the 3rd, and x squared y to the 3rd times x squared y to the 3rd squared. So let's leave the numerator alone. And let's look at this. Remember, we assume there's a 1 there. And so I have a product of something in the parentheses. They're the same, so the base is the same. So that means that we take x squared and y to the 3rd, and we add the exponents. And then we have y, x and y to the 3rd. Now we apply the quotient rule that says that if I have a division of the same base, I can write that as a subtraction of the powers. So we have 3 minus 3, which is x to the third, x squared, y to the third of 0, so that's 1. So that means that x squared y to the third divided by x squared y third times x squared y third to the 2 is just 1 in every case. No matter what values of x and y you plug in there, it would always equal 1. So now we're going to look at some negative exponents. The general rule here, I'm using a base of a again, a to the negative n, we can think of as being 1 over a to the n. Effectively, we take the negative exponent and we put the base and the exponent positive in the denominator of a fraction. So an example, and you can see we're sort of stacking rules now. So the first thing we need is the quotient rule. So we have 4 minus 7 is x to the negative third. And then the above rule says, well, I can write that as 1 over x to the third. These are equivalent expressions. If you go on and take calculus or look at calculus or study calculus, sometimes it's advantageous to have x to the negative third power. Sometimes it's better to have x to the third in the denominator. So why does this happen? Let's look at the same example, but let's take this more literally. We have x to the fourth, which means that we're multiplying the base 4 times. Same with the denominator, we're multiplying the base 7 times. And this is a situation. Now, just straight cancellation law says I can, for every 1 on top, I can get rid of 1 on the bottom. So let's get rid of this guy, 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 this guy. And we're left with 1 over x times x times x, which is really x to the third. So that's why when we do the quotient rule and subtract and we get a negative exponents, it's the same as if we have spell those out as a product, cancel, and we get x to the 1 over x to the third. So that's the y. A lot of these are just shorthand. The quicker way to handle exponents, that's sort of why we're reviewing this, is it's easier when we're looking at polynomials or we're trying to graph things and we have a bunch of powers and we want to simplify or expand. These are quick ways to handle those things. Let's look at another example. Again, this lecture is going to be heavy on examples. And let's say we have negative 5x to the 2 of 9. So it's negative 5x squared to the 4 minus 9. So negative 5x squared to the negative 5 is 1 over negative 5x squared to the 5th. Not too bad. Just applying the rules. You can always pause, go back, and look at these examples again. Really helpful. The rule is nice. You can state a rule, state a definition, theorem, corollary, lemma. It's always nice to see the application. I think it sinks in a little bit better. So this is product rule. Product rule says we add the exponents when they have the same base. So we're going to add this, which y to the 2 plus negative 8 is the same as 2 minus 8, which is the same as negative 6, which is the same as 1 over 6. So that's the negative exponent rule. Pretty straightforward again. Exponent reviews are helpful. These are maybe stuff you would want to review even as you head on to more advanced mathematics. If you take a Calc 1 or Calc 2 course in college, it's nice to review these. All right, the power of products, which means if I have two bases, a times b, and I'm taking that to some power n, the power product rule says I can take each individual to the same power. So a to the n times b to the n. An example, xy squared is the same as x squared, y squared. So why is this true? Again, let's recall what we're doing when we're squaring stuff. We're multiplying it by itself however many times the power indicates. So in this case, we're multiplying x and y and x and y. Now in lecture 1, we talked about some of the properties of real numbers. We know that it's associative and distributive. So I can get rid of these brackets and write this way. That's the associative. Now the commutative says that I can arrange these this way. So the commutative property allows us to do that. And x times x is just x squared, and y times y is just y squared. So again, this is a shorthand. Xy squared, power of products, this gives us x squared, y squared. The y is the longer process on bottom, knowing that we're doing the associative rule and we're doing the commutative rule to get up to the same result. Let me write that just so we know. We use associative and commutative properties. And refer to lecture 1 in this series. If this is not familiar to you, we go over that in that lecture. So let's look at another example. Again, we'll try to mix some things in here so it looks a little bit more hairy. So when we're spelling out the rules, it makes a little bit more sense. So I have a product 2 times x squared times y to the third. Now the rule says I can take to the fourth power each of these terms individually. And I'm going to be careful how I write this. Don't be afraid to use brackets. You're not going to get penalized for bracketing things, especially when you're starting out. Now I'm just going to leave that as 2 to the fourth. Now the rule says I take x squared to the fourth is our previous rule that says now I multiply those two things. Same with y to the third to the fourth. I multiply those. So we get 2 to the fourth times x to the eighth times y to the 12th. And 2 to the fourth we can evaluate. 2 to the fourth is 2 times 2 times 2 times 2, which is 16. So these are equivalent expressions. It might be a little clearer, 16x to the 8th y to the 12th, than what we had before. And that's sort of the goal of this section, is just to take exponents and handle them so they look a little bit more manageable. That's relative, of course. Sometimes it might look worse, but that's math sometimes. Another example, we're going to mix in some other ideas that we just explored. So I'm going to apply the rule literally, meaning that I have this quantity of products taken to the -2. So I'm going to take each to the -2, being very careful of how I write each term. And once you're good at this stuff, when it's a little bit clear to you, you don't have to do intermediate steps like this. Now, the rule says I take 2 times -2. I'm erasing. times x, now I multiply -2 and -2, times y, and I'm multiplying 3 and -2. So we got 2 to the -4 times x to the 4 times y to the -6. Now, the negative exponents we can write, so this is x to the 4th stays on top, and we know that 2 comes down and 4 stays positive, y to the 6th. So this is x to the 4th, 16, y to the 6th, which is much better looking than this. Simplification in this case is very, very warranted. Let's do an example with some more variables. Again, another look. So let's say we have f g to the 3rd to the 5th, and then we have f times g 2 to the -2. So I'm going to do the numerator and denominator first using this rule. So being careful, I'm going to write it with brackets, each individual term to the 5th. Do the same to the denominator. And again, once you get a little bit quicker at this stuff, there might be a lot of these steps in between can go away and make your life a little bit easier. So now I'm multiplying them. So 2 times 5, that's the rule. 3 times 5, f -2, and then g -4. Now the rule says I have the same bases. They're in a quotient, so then I can add the numerator exponent and the denominator exponent, or subtract, my fault. Minus -2 times g to 15 minus -4. So 10 minus -2 is the same as 10 plus 2. G to the 15 minus -4 is 15 plus 4. So this is f to the 12th times g to the 19th. Again, this is much, much prettier than that. All right, next we have what's called the power of quotients. This says that if I have a fraction that's raised to some power, let's say m, maybe a little bit clearer here. So I have a fraction raised to the power of m that I can take the power to each individual base. So let's look at an example, and then we'll look at why that's true. So I have xy squared will be the same as x squared and y squared by this rule. So why is that true? Again, this is going to be a shorthand, right? We're taking x over y and squaring it, so we're multiplying it by itself twice. Then we're using associative laws. We're writing it this way, which is x squared, y squared. So you can always apply the rule literally and then work from there, and you'll see that you'll get to the same spot. But the quotient rule here is the power of quotients are a little bit quicker. Let's look at another example. Let me clear this a little. So we have x and x to the 3rd to the 5th. So we'll do this literally just to apply the rule that we just learned. So that means I take x to the 5th and then x to the 3rd to the 5th. Again, we're just stacking laws here. So this is 3 times 5 by the rule. And let's go a little further, because we know that if I have the same base, that I can subtract. And then we get -10 And the other rule, the negative exponent rule, says that we can take this as a power in the denominator. So this is x to the 10th. So what we're saying is that these are exactly the same. There might be some situations where you prefer x over x to the third to the fifth. There's also different ways to which to simplify this and the order in which we simplify. I'm just applying that rule directly. All right, so let's put all of this together and look at simplifying exponential expressions. The concept of expressions, I think we went over in lecture 2, the difference between an algebraic expression and, say, an algebraic equation. So we're going to use the laws, or use the things we just learned. So we have something like 9x to the negative 5th, z to the 3rd. We're going to multiply that by 3x to the 4th, and z to the negative 4. All right, the first thing I want to do is I want to group this a little bit better. We have the distributive property from lecture 1 or 2. So I'm going to group 9 times 3. And so this is distributive, associative, commutative, all of these real number properties. So I get x to the negative 5th and x to the 6th. We got z to the 3rd times z to the negative 4th. You do erase. All right, so 9 times 3 is just a constant, 27. And the rule then says that if I have two bases that are being multiplied, I can add them. And then we're going to add 3 plus negative 4. So we get 27x. I'm not going to write the 1. Negative 5 plus 6 is 1. But we'll just leave it that way. 3 plus negative 4 is negative 1. We're going to, again, use the rule that negative exponents we can put in the denominator. So this is 27x divided by z. Another perfectly reasonable way to write this would be 27 times x over z, whatever your preference might be. But just using the rules, using our properties of real numbers, we get the simplification 27x over z, which again, much better than that expression. Another example, mix up some variables and keep using x, y's, a's, and b's. What's h and j? So 7, h negative 1, j squared squared. I'm going to apply the rule on the numerator and denominator, literally moving 4 to each, being careful with my notation. Do it here as well. I tend to write a lot when I'm doing examples, but even when I'm doing my own mathematics, I tend to write a lot just so I have a clear path of where things are going. 2 to the 4th, again, is 16. h2 to the 4 means that I multiply 2 and 4, so it becomes h to the 8th. 2 times 4 is 8. J to the 1 times 4 is the same as 4 times 1 is 4. And we have 49. Negative 1 times 2 is negative 2, and 2 times 2 is 4. I'm going to put the numbers, the constants out here. And then let's look at, we have h base, h base. It says the rule that I take 8 and I subtract it from the power of the denominator base. Same with j. 4 minus 4, so we get 16 49ths. 8 minus 2 is 10 times j to the 0. And recall that anything raised to 0 is 1. So this is 16/49 times h to the 10th. Again, much prettier than the original expression. Much easier to handle, much easier. If I want to replace h and j with some numbers, some real numbers, I can do so in the original, but you can see in the simplified version, replacing h is much simpler in this case. Still raising something to the 10th power can be tricky. Nevertheless, it always looks easier. And you can notice j drops out. So j will always cancel regardless of what real number we pick for j, it will always cancel. All right, let's look at one last example. Let's say b squared c to the negative third divided by b to the negative third. We'll say quantity. Let me be careful how I write these brackets, because we want to be able to make sure that it's clear that what I'm doing is I'm taking this quantity to the 2. I'll put this down just for convenience. Now, the rule says, again, I take b squared c to the negative third squared divided by negative b, no, not negative b, b to the negative 3 squared. And then I multiply 3 and 2. So we'll take this little by little. So that's negative 6. And then I multiply this guy, that's b negative 6. Now I have a product and a power. So I'm going to take each individual term to that power. Being careful, again, to keep my terms straight. And then b to the negative 6. So we have a negative 6. B is 2 times 6, so b becomes negative 12 times c to the negative 6 divided by b to the negative 6. Now I have the same base b, so let's do that. We know that we subtract the denominator base power from the numerator, and then we have this. So again, a to the negative 6 times b, we're going to have b to the negative 12 minus 6 will be negative 12 plus 6, which is negative 6, and c to the negative 6. These are all negative exponents, so let's move them all to the base, or the bottom, sorry, 6, b6, c6. Which we can be done, or we can be cute and be like, well, that's really just a, b, c to the 6th. And since 1 to the 6th is just 1, I can actually write this as 1 over a, b, c to the 6th. Any of these are a conclusion point. Again, it depends on your professor, depends on what the question was asked, depends on what you want to do, but that's it. A much simpler expression than what we started out with. As you can see, the very ugly quotient becomes something much more manageable, especially if we are replacing a, b, and c in this expression to evaluate it. So that's the end of this lecture. Next time, lecture 4, we will be doing radicals and rational exponents, which will require us to remember the laws that we learned in lecture 3. So next time, radicals and radical exponents. So thanks for watching, like and subscribe, and I hope this helps. Hello, this is lecture 4 from the College Algebra OpenStax book. using that as a guide. We are in the first chapter in section 1.3. It'll be radicals and rational exponents. Lecture 3, we did all of the laws of exponents. So if you don't feel like you're comfortable when we talk about rational exponents because you don't remember some of the rules, check out lecture 3, which is just about exponents. And that will be helpful for you to go back. So I'm going to assume that you know basic laws of exponentiation, exponents. And I won't go over that ground too much again. So we're going to start with the notion of a radical. I don't know where the term radical comes from. I didn't look it up. But it's a root. And we'll first talk about square roots. And the symbol, this, which I don't always draw very well, this is called the radical. The number underneath is called the radicand. And the whole thing is just a radical expression. Now, when you see the symbol without a number there, it's assumed to be 2. So just the radical without number, we're assuming square root. So if we have the square root of 25, now most of you might be familiar with, is 5. Why is this? You always want to know why in math. Why is this true? Why does this rule say that the square root of 25 is 5? So what a root essentially does, it wants to know 2 numbers that multiply that give me the radicand. It wants to know if I can evaluate the radical, I need 2 numbers that multiply that give me 25 that are the same number. If that's true, I can evaluate it. You can evaluate any radical. You'll get a decimal, stream of decimals. In most cases, it'll be ugly, so we like to simplify by keeping the radical so it's a little bit cleaner. But the gist is this. 5, I'm going to break down into its prime factorization. The nature of integers says that they can always be written uniquely as a product of primes. So 25 is 5 times 5. 5 is prime, so I can't break it up any further. That's the nature of primes. So 25 is the same as 5 times 5. The rule says if I have 2 numbers multiplied together, in this case I need 2 of them, right? Because it's a square root, that I can evaluate it by taking 1 of them out. And we'll get to higher roots later in this video. So let's look at some goofy stuff. What's the square root of 81? So let's look at the square root of 81. It's 9 times 9 is 81. So I know I can write the square root of 81 as 9. And 9 is 3 times 3. So 2 numbers that multiply to give me 9 is 3. So this evaluates to 3. Another quick example is we can do arithmetic with roots, just like we can any real number. These are real numbers, so we can add, subtract, multiply, and divide them. There'll be some rules we'll see later what we can do and when. Now, the square root of 36, if I want to look at a factorization, it's 6 times 6. Well, I just need 2 numbers, but if I needed to break this further, it'd be 2 times 3, 2 times 3. I can bring out a 2, I can bring out a 3, but all we really need is 2 numbers that multiply to give me 36. That's 6. Same with 25, it's 5 and 5. So that's minus 5. So it's 1. Okay. You become pretty quick at square roots when you recognize something about them. Let's look at the squares of the first 10 integers, positive. I don't know why I skipped 6, but let's go back. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, 64, 81, 100. All right, so the integers from 1 to 10 squared, the results are called perfect squares. So notice then that 1 is 1, 4 is 2, 9 is 3, 16 is 4, 25 is 5, 36 is 6, 49 is 7, 64 is 8, 81 is 9, and 100 is 10. Because when we take the square root of a perfect square, we get a perfect integer back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the first 10 perfect squares. Once you know that, you can recognize the square roots a little bit quicker, and especially when you're simplifying them, reducing them, knowing this chart helps, right? All right, so let's get into some rules. In our previous lecture on exponents, we also had a product rule. The product rule says if I have the square root of a times b, I can separate these into 2 separate square roots. I tend to hook the root radical symbol just so I don't have things, if I'm writing x times the square root of 4, that it's clear what's inside and outside. So sometimes I'll hook it because I can get sloppy. So product rule says if I have 2 things inside that are being multiplied, I can separate them into 2 separate radicals. An example, let's say 50x squared y to the 3rd of z. So I can write this as square root of 50 times the square root of x squared times the square root of y to the 3rd times the square root of z. All right, so that's rule number 1. We can reduce them this way. Now let's look at 50. Remember, if I can evaluate 50, I want to do so. So I know this is 2 times 25. And it's 5 times 5. So that's its prime factorization. 5 times 5 times 2 is square root of 50. So I can write the square root of 50 as 5 times 5 times 2. Since it's a square root, I want 2 numbers that multiply that give me 25 in this case. I can evaluate that. In other words, I can bring it out. 2 does not decompose that way. We can't have 2 numbers that multiply that give me 2 that are the same number because 2 is prime. So 50 becomes 5 square root of 2, x squared. This is an important property that the square root of a square is always just itself. And the reason is because the square root of x squared is the square root of x times x. And again, the rule says if it's a square root, I need 2 numbers to multiply that give me that number, in this case, x. So this is x. What about y to the 3rd? So we have the square root of y to the 3rd, means we have the square root of y times y times y. So again, I'm going to bring out a pair, which means I bring out a y, but I have this single y here, and I have to leave it inside because it doesn't have a pair. So we have 5 square root of 2 times x times y square root of y times square root of z. That's perfectly fine to leave it that way. It looks a little ugly to me. Remember, the product rule says I can combine the products inside. So I'm going to take what isn't inside and put out here 5xy. I'm going to take a square root, and I have 2yz. So this simplifies to this. All right, we have a product rule. We definitely have a quotient rule. And if you are watching this series, you'll know from a previous lecture that you guessed it, this is going to be a divided by b, take the square roots. It's the same as taking the square root of the numerator and square root of the denominator. No surprise. Let's look at an example. Square root of 7/64 is the same as square root of 7 divided by the square root of 64. Remember, if I can evaluate, I want to write the square root of 64 if I can as a number, square root of 7 too, but square root of 7 is ugly because 7 is prime, so we'll just write it like that. 8 times 8 is 64. It's one of our perfect squares, so this simplifies the square root of 7 divided by 8. Let's look at another example. We're going to have a lot of examples in this section. I don't think it helps just to write the rule. Having the rule and showing some examples helps to sort of stick in your head of why things are happening. We're going to write this as a numerator of 2a squared and the denominator of 9b to the fourth. The product rule says that we can write this as the square root of 2 times the square root of a squared divided by square root of 9. I don't know, that looks like an a to me. Sorry about that. 9 times the square root of b to the fourth. Now, the square root of anything squared is itself, so this is just a. Convention says we like to bring out the constants without roots in front of the radical. Just it's easier to see. And this will be b to the fourth times 3, but b to the fourth is the same as b times b times b times b. So for every 2, because it's a root, I bring out a b. So this is b squared. And that's it. A square root of 2 divided by 3 times b squared, which gives us the simplified version. So again, these are real numbers. So radicals, we should be able to add and subtract. And we'll start with the square roots. So the rule for adding and subtracting square roots is that the radicand, the thing under the radical, has to be the same. An example is if I have the square root of 5 plus 2 times the square root of 5, these are the same, the radicand are the same, so I can write this as the sum of the coefficients. So again, we have out here, we have 1 assumed, then it's 1 plus 2 is 3 square root of 5. It might not be that obvious. The why it's happening is I don't want to get too far ahead of the course, but I could factor out these terms. They're like terms. So I can take out the square root of 5, and I'm left with a 1 here and a 2 here. And I get square root of 5 times 3, which is 3 square root of 5. So it's undistributing the square root of 5, so to speak. Factoring is undoing distribution. So another way to think about this is that if I am adding these two things, the multiplication in front says I have 1 square root of 5, I have 2 square root of 5s. And if I add those, then I have 3 square root of 5. It's just another way to look at it. Another example maybe would be, let's use some variables. 2 square root of x minus 5 square root of x. Now the rule says if I have the same radicand and the same root, in this case square root, well, I'm just going to subtract the coefficients 2 and 5. So 2 minus 5 is negative 3 square root of x. Simple enough. Another example, the square root of 5 plus 6 times the square root of 20. Now notice that square root of 5 and square root of 20 aren't the same. Or are they? Well, let's see if we can reduce 20. Now 20 is 2 times 10, which is 2 times 5. So the prime factorization of 20, if I were to write 20, I can write it as 2 times 2 times 5. The square root says I need a pair that multiply. So that means I can write this as 2 square root of 5. So the square root of 5 plus 6 square root of 20 is equal to the square root of 5 plus 2 times 6 times the square root of 5, because I'm replacing 2 square root of 5 with the square root of 20. Now I'm just going to add though, or multiply 2 and 6, that's 12 square root of 5. Now I have the same radicand, the same root square, and I'm just going to add the coefficients. 1 plus 12 is 13 square root of 5. So that's the rule for adding and subtracting. We have to make sure that we have the same radicand and the same root. If I just the cube root of x and the square root of y, I can't add those. They're different roots, even though they're the same radicand. They're the same thing under the radical sign. Square root of x plus the cube root of x is equal to the square root of x plus the cube root of x. Can't add. This is a cube root. This is a square root. They have to be the same roots. All right, let's look at something useful. Let's call it rationalizing denominators. It's best to, let's look at an example and see what we're doing. So when we say we want to rationalize something, we have the square root of 5 divided by 2 times the square root of 10. So we want to rationalize means I want to get rid of this root in the denominator. I want this to have all of the roots radicals on top, and on the bottom, I just want a number. This should be easier for us to handle doing that. So how? How do we rationalize? When it's a single term, 2 times the square root of 10, we multiply by the square root of 10, the top and bottom. So this would be true if you have a single term you want to rationalize, you always multiply by the radical that's in the denominator. So we're going to multiply by the square root of 10. You might be asking yourself why, because this doesn't look easier. But let's look at the steps. I'm just going to write it using our rules. And you should see down here that I have 10 times 10, which means I can evaluate that as 10. Two numbers that multiply that give me 100 is 10 times 10. So I bring out a 10. This is 10 times 5. Well, 5 times 2 is 10, so I can write this like this. This is 10, 5 times 2. So what I have then is I have 5 times 5 times 2. I can bring out a 5, and the square root of 2 stays, and this is 10. Of course, we can simplify 5 over 10 is the same as 1/2. So this is the square root of 2 over 2. So why is this useful? I will say in most mathematics, it's easier to handle rationalized radicals than not, especially in calculus. Any computational mathematics, having the radical in the numerator is easier and more straightforward. I might be overstating that a bit, but I find in calculus that when I help students or with calculus and we have some function with radicals, in the numerator, you can write them as rational exponents, which we'll get to shortly, and it becomes easier to handle taking derivatives and looking at integrals and so on if you go that route. Otherwise, it's just prettier. I mean, honestly, square root of 5 divided by 2 times the square root of 10 is ugly. Square root of 2 divided by 2 is pretty, in my opinion. So let's look at some more. So I want to rationalize that. Now I just have a variable. I have y and x. The rule's the same. I'm going to multiply the top and bottom by the square root of y. This becomes 3 times the square root of x, y. Product. This is 4. Now I have y times y. Remember the rule, this becomes y. So this is 3xy divided by 4y. Now, it's not simpler. It doesn't look simpler, the two expressions here, but it is rationalized. So what do we do if we don't have a single term on the bottom? What if we have something more complex that's not just a single term? Let's say we have something that looks like this. 1 plus the square root of 5 in our denominator, 4 in our numerator. How do we rationalize? If we just multiply by the square root of 5, we won't have eliminated the radical in the denominator. If I multiply the denominator by the square root of 5, if I distribute this, I get the square root of 5 plus the square root of 5 times the square root of 5 is just 5. So you can see I still have a square root in the bottom, so that's not rationalized. So what do we do? Well, there's one of the prettier words in mathematics is we use the conjugate and multiply the top and bottom by it. So what is a conjugate? Well, I use the same expression. Let me rewrite this here. I'm going to put brackets. I'm going to multiply by the conjugate is the same expression, but I reverse the sign. Meaning I take, if it's an addition, I make it subtraction. If it's a subtraction, I make it addition. The reason is that when we multiply through, and I want to be careful. I keep doing that. It's not all under the radical. I'm just rewriting it. I'm not actually doing anything to it. 1 minus the radical. Now this and this is an upcoming lecture review. We would FOIL this. It's a form of distribution. We multiply the first terms, we multiply the outside terms, we multiply the inside terms, and we multiply the last terms. And doing so will get us a four terms, which the middle will drop. So if I did this literally, 1 times 1 is 1. 1 times the outside, -5, that gives me the square root of -5. -5 times 1 gives me the positive square root of 5. And then square root of 5 times square root of 5 gives me 5, but it's negative. So you can see that, again, we'll go over FOIL in future lectures. But for now, you can see that these middle terms drop, and I have 1 minus 5, which is -4. 4 divided by -4 is just -1. 1 minus square root of 5, that's -1, plus the square root of 5, which, you want to be nice, it looks better this way. All right, so conjugate is useful. It helps us rationalize. Now this and this are the same expression. One is a little bit more clear. 4 divided by 1 plus the square root of 5, square root of 5 minus 1, I think is a little bit clearer. Next, let's go on to things other than the square root. So far, we've been dealing with the square roots. Remember, if there is no number there, we assume a 2. But we can have what's called the nth roots. And n could be any number, any integer. So n is an element of the integers, meaning n is 1, 2, 3, 4, and so on. And the reason we don't write the square root of 2 is it's most common. So other roots we write so we can differentiate. We call this the cube root. This we just call the fourth root. The fifth root, you guessed it, fifth root. So we always write the roots when it's not 2. So these work exactly the same as square roots in sense of how do we evaluate. So for example, if I have the cube root of 27, now I need 3 numbers that multiply together that give me 27 if I can evaluate. So 27 is 3 times 3 times 3. Since I have the cube root, I need 3 numbers that multiply that give me 27. So this evaluates to 3. Let's use something larger. Let's say the fifth root of 32. We need 5 numbers that multiply that give me 32. I'm picking nice numbers, by the way. It's 2 times 2 times 2 times 2 times 2. So if there's 5 of them, I could evaluate that as 2. Of course, your calculators will handle this, but this is what's happening. Again, we're taking out 5 numbers that multiply that give me the radicand. It helps when we're simplifying. So same principles apply. Let's look at another example. So we can add and subtract using the same property. The first thing I look at is if I want to subtract these, I need the same root. So we have the fourth root of 3 and the fourth root of 48. So the roots are the same, but I don't have the same radicand, do I? Well, let's look at what 48 can reduce to. If I want to put this in prime factorization, easiest if it's even, divide by 2. You can go straight to what you probably know it should be, but that is 2 times 12. This is 2 times 6. This is 2 times 3. So that means the fourth root of 48 can be written as the fourth root of 2 times 2 times 2 times 2 times 3. So 4 of these means I bring it out, and I'm left with the fourth root of 3. So that means the fourth root of 3 minus 2 times the fourth root of 3. Same roots, same radicand. I subtract the coefficients. 8 minus 2 is 6, the fourth root of 3. I would recommend writing your roots, if you're doing this by hand, as small as you can so you don't confuse yourself, that I'm not multiplying 6 and 4 at the end here. All right, so let's bring the last lecture and this lecture together by looking at what's called rational exponents. So what's a rational exponent? Well, it's a way to write a root. If I have the nth root of a raised to the power of m, I can write this as a raised to m divided by n. In other words, I take the root is the denominator and the power of m is the numerator of a fraction. Let's look at an example real quick. So the cube root of x squared is x 2/3. The root is always the denominator. The power of the radicand is always the numerator. The square root of 7, we can also write as 7 to the 1/2. So this works both directions. I can always write a rational exponent as a root. So let's make a note real quick of a key fact here, and we'll explain why it's true. Now above I said that this is the same as the nth root of a to the m. It also happens to be the same thing as the nth root of a quantity to the m. Now why is that true? It's convenient. We're glad it's true, but why is it true? Let's look at an example. Let's say x to the 2/3. So I know I can write that as the cube root of x squared, which is the same as writing this as the cube root of x times x. The product rule says I can separate these. And then literally this is the cube root of x times the cube root of x, which is the same as saying cube root of x squared. So these two things are exactly the same. It might not seem that way, but this is why. And sometimes it's much easier to write the external square than the internal square, depending on what it is you're trying to do or simplify. So let's look at a case where that might be true. Another example. Say we have 343 to the 2/3 power. And we want to know, what is this number? Is this a number that we could evaluate just off the top of my head? Looking at it, it's like, this is not pretty. Well, let's apply the rule. We know this is the cube root of 343 squared. Now, I don't want to square 343. That's 343 times 343. But I know I can write it this way. It's a cube root of 343 squared. Is that better? Well, let's break down 343. So it happens that it's 7 times 49, and 49 is 7 times 7. So I can write this as the cube root of 7 times 7 times 7 squared. Now, the cube root means I need 3 numbers and multiply. That means I bring out a 7. So 343 raised to the 2/3 power is actually the same as 49, which is nice. It's easier to do. You can put that in your calculator. You would get the same number. But if you had to do it by hand for whatever reason, on an exam, on a quiz, and homework, that's how you would do it. All right, so let's look at simplifying rational exponents. So we had a rule in lecture 3. And again, I said I wasn't going to do too much, but let me write this real quick. If I have two bases that are same, to raise to some power, I can write the power as an addition of powers. The same is true as if I have the same base, but with a fractional or rational exponents. This is the same as 1/2 plus 3/4. Now I need a common denominator, so I have 2 over 2 plus 2 over 4. I'm trying to erase, I swear. So that's 5/4. I can also write this as just the 4th root of x to the 5th if I wanted to. Notice that this would be x times the 5th root of x because I have 5 of these, and the 4th root says I take out 1 for every 4 and leave the last. So yeah, that's that. If I have something like this, I'm going to write it like this again, x to the 5th. And I don't want to take the quantity, so let's just look at what this is. Remember, it's a 4th root, so I need 4 numbers that multiply that give me what I need. There's 4 here, so I bring one out, and I have the 4th root of x. All right. Another example, rational exponent, simplifying. I can write this as a square root, 9/16. The quotient says I can take the numerator and denominator. I know 9 is a perfect square, it's 3 squared. I know 16 is a perfect square, it's 4 squared. So that simplifies 9/16 to the 1/2 is the same as 3/4. All right, let's look at a complicated problem. And complicated, I just mean it just looks nasty. Hopefully I won't make too many mistakes. So 250x squared, the square root, divided by 100 b to the 3rd. My paper's flying. Let's say 7, the square root of b, divided by the square root of 125 x. So we're multiplying these. They're all square roots. So let's look at 250. Let's do some reductions here. That's 250 times 10. That's 5 times 5. This is 5 times 2. So the square root of 250 we can write as 5 times 5 times 5 times 2. Now it's a square root, so I just need 2 and bring out the 5, but then I have this left. So this actually simplifies to 5 square root of 10. And x squared, the square root of x squared is x. So 5x square root of 10 is the numerator. Now we know that 100 is a perfect square, so that means we're going to have 10 because 10 squared is 100. And b to the 3rd square root is going to be b square root of b. Why is that? Because b times b times b gives me b to the 3rd square root. I take out the pair. So that leaves me with 10b square root of b. Let's leave 7b alone here. Now, what about 125? Well, 125 is 5 times 25. It's 5 times 5. So 125 can be rewritten as 5 times 5 times 5. Square root means I take out for every 2. So then I get 5 square root of 5. And I have this x here. All right. So I wrote a lot. So let me move this down here. 5x square root of 10 divided by 10b square root of b times 7 square root of b, 5 square root of 5x. All right. So I notice here that I have a 7 square root of b. I'm going to divide that by 10b square root of b. And I'm going to put the 5x square root of 10 divided by 5 square root of 5x. Again, these are properties of real numbers in lecture 2, I believe, if you need a refresher of why I can move stuff around that way. So the square root of b divided by the square root of b conforms to our rule that if I take 1/2 and b 1/2, I'm converting them to rational exponents. The law of exponents says that if I have a quotient, that I subtract the power of the numerator from the power of the denominator. This becomes b to the 0, and anything to the 0 is 1. It's a fancy way to say that b's cancel. So this becomes 7, 10b. Now we have a 5 here, so 5 and 5 cancel. Then we have x square root of 10 over 5x. So let's put all this stuff together. 7x square root of 10 divided by 10b square root of 5x. We could stop there, or we notice that we have a radical in the denominator, and we've been told we don't like those things. So let's multiply it by 5x square root top and bottom. This gives us 7x 10 times 5x by the product rule. This gives us 10b. Now 5x square root will give us 25x squared, which is 5x. So this becomes 7x square root of 50x divided by 50 bx. So we're using a lot of rules. We're using a lot of the properties of real numbers. Notice here that we can cancel this x. So we have 7 square root of 50x divided by 50b. Now what about 50? Can we reduce 50? Well, it's 25 times 2, 5 times 5. So that is 50 square root is going to be 5 times 5 times 2, which is going to be 5 square root of 2. And we have to leave the x, so this becomes 7 times 5 2x divided by 50b. Well, this 5 goes away. This becomes 10. So we have 7/10 2x b. So 7 times the square root of 2x over 10b. Did that quick? Check me out. Let me know in the comments if I made a mistake. It's possible I go quick. But that's pretty much all we wanted to talk about for this lecture. So that's radicals and rational exponents. The next lecture will be on polynomials. If I could spell it. So we start getting ever closer towards the beginning of the college algebra course. Polynomials are the heart of college algebra. So we will take a look at those next time. Thanks for watching. Like and subscribe if you can. It helps me out. And I hope you have a nice night. Thanks. Hello. Today we're continuing with the college algebra lecture series. This is lecture number 5. And today we will be talking about polynomials. And hopefully after the video, you'll be able to identify the degree and leading coefficient of the polynomial. You'll be able to add and subtract polynomials. You'll be able to multiply polynomials. You'll be able to use FOIL to multiply polynomials, and you'll be able to perform operations on polynomials with several variables. Now, I'm taking the examples and the basic structure of this review from the OpenStax College Algebra 2nd edition, which is free to download, PDF version. There'll be a link in the description. This is section 1.4 from the prerequisite section. So really, these first 5 or 6 lectures, I think 7 lectures, will end up being all review for a college algebra course. So this is good if you are going into a college algebra course. These are the things you would need to know, the prerequisite, so to speak, of the class in most cases. Now, your lecture, your course, your professor might assume different things that you might know, but this is generally the stuff you would need. So let's begin by just defining what a polynomial is. So definition, we'll say a polynomial is an expression of the form, and this is going to be very general, ax to the n, a sub n minus 1 to the xn minus 1. And this will continue to a sub 1 x to the 1 plus a sub 0. Again, this is very abstract, very general. Here, each of the a sub i's is called a coefficient. Coefficient is a math term that means the number in front of the variable. So for instance, if we had 2x squared, 2 is the coefficient, and there's a number in front of x squared. And a sub 0 is constant. It isn't being multiplied by a variable, so we call it constant. The x's, the xi's, let's say, are variable, or variables, each one. Meaning we can replace these x's with some real number, and then the expression, the polynomial expression, will have a value. All right, so we got coefficient. Let's look at what's called the leading term, or a term. So a term of the polynomial are the AIXI in the poly. Is. So an example, I have 3x squared plus 2x plus 1. Each of these we consider to be a term in the polynomial itself. So that's what a term is defined as. The leading coefficient or leading term is the term with the highest degree. The highest power. And the coefficient of that term is the leading coefficient. So our example here, 3x squared plus 2x plus 1, the leading term is 3x squared, and the leading coefficient is 3. X squared is the highest power, 2. X has 1. And sometimes we can think of this as x to the 0 because x to the 0 is just 1. You could look at our previous lectures to get a better grip on the exponents. But that's the leading coefficient in our example. So the first thing we can do is identify some polynomials, and will lead us to our first example. 3x squared plus 3x cubed, let's say. 2x squared plus x plus 4. So let's identify the leading term. And I put them in descending order, so it's going to be 3x cubed. The leading coefficient, I'm just going to write COEFF. That is 3. And now the degree of the polynomial is the power of the leading term. We call this the degree of the polynomial. So in this case, it's 3. So we have a degree 3 polynomial. This becomes useful later in the college algebra course, knowing the degree of the polynomial. It gets an idea of how many solutions we might have given a polynomial equation. There's also some other useful things about degrees. Degrees will tell us what a graph of the polynomial looks like. A degree 4 has a pretty distinct graph. You can identify a degree 4 poly or degree 3 poly or degree 2 poly. Just by looking at a graph, you can tell what degree it would be. So that comes later in the course. Let's do another quick example here. 19x plus 4x squared plus 4 plus x to the 5th. So here I did not put them in descending order. So the leading term is the term of the poly with the highest degree or highest power. So that's x to the 5th. What's the leading coefficient here? Well, we assume that if there's no visible number in front of x to the 5th, we're going to assume that there's a 1. So x to the 5th is the same as 1 times x to the 5th. Often in math notation, we do not write the most common or obvious. You might have noticed in logarithms, if we were a log of 4 and there is no base, we assume 10. X assumes a power of 1, and no number in front of a variable like x to the fifth, we assume that the coefficient is 1. So the degree of the polynomial is 5. So we have a degree 5 polynomial. And again, the degree 5 will tell us a little bit of what the graph might look like if we were to graph it. And that comes later. All right, let's look at how to add polynomials. It's good to start with the example. There isn't much to this as far as definitions or theorems or corollaries or lemmas. We're just going to take two polynomials, add them. So the key here is like terms. When we're adding or subtracting polynomials, we can only add and subtract like terms. Like terms, again, the term, this is a term, this is a term, this is a term, this is a term. There's 4 terms here. And we have to match variables and match power. So an example, if I have a variable of x, I can only add variables that have x. If x is squared, I can only add variables that have a square. So the like terms mean it has to look the same. They have to look alike. So the first thing we're going to do then is combine like terms. In the previous lecture video here, we did commutative addition in real numbers. So this is why we can combine like terms. The addition's commutative. So I see I have a 12x squared. And over here, I have an 8x squared. So I'm going to put those two next to each other. Then I have a 3x. I don't have any other x's, and I have a 19. That's it. We combine like terms. And now we can add those that are the same. The only thing here that's the same is the x squareds. And so we're going to add the coefficients. So 12 plus 8 is 20 plus 3x minus 19. So that's it. That's all we can add. We can't add 3x and 19 because 19 does not have an x. And we can't add 3x to negative 19 because, well, 3 has a variable. So let's do something a little more complicated. Let's say 7a cubed plus 6a squared minus 4a minus 13. I'm going to group those and add that to negative 3a squared minus 4a. Nope, this should be cubed. 4a squared plus 6a plus 17. So the first thing you want to do, again, is combine like terms. I'm going to underline with one line the things that look alike that have a cube. So I got 7 cubed and 3a to the third. Now I'm going to bring the sign. So if there's a negative sign in front of 3, I'm bringing that with. If there's a positive, I'm bringing that with. So that's all of the cubes I can see. I'm going to put 2 lines under the square. And those are all the squares I have. So I'm going to write them 6a squared minus 4a squared. I'll put 3 lines under the a. You can cross these out. You don't have to underline, or you don't have to do anything, just as long as you keep track. So here's the constant terms, negative 13 plus 17. So now you see I grouped them nicely into like terms. So then we do 7 minus 3 is 4, a cubed. 6 minus 4 is 2, so that's 2a squared. Negative 4 plus 6 is positive 2a. And negative 13 plus 17 is the same as 17 minus 13, which will be a positive 4. So that's it. That's as far as we can go. We have a cube term, a square term, a term, and then a constant. So there's no more like terms. So this is it. Now subtracting polys is the same as adding. We need like terms. But one difference here is I'm subtracting a polynomial from another polynomial. So an example is 2x squared plus 3 minus x squared minus 4. So in other words, I'm subtracting from 2x squared plus 3, x squared minus 4, the entire polynomial. Now, in a previous video, we talked about how we can think of in the properties of real numbers. If I have x we have x minus y, let's say. I can think of this negative as being a negative 1. So it's the same as adding negative 1 times y. Now you might ask, why would I complicate that if I'm just subtracting two things? Well, it's for this particular case. Now, you don't have to do this every time once you're comfortable, but I'm going to write it as an addition problem. I'm going to turn that negatives into a negative 1. And I'm going to do this to illustrate the distribution of negative 1 through the term x squared minus 4. Because when you subtract a polynomial, you're essentially subtracting each term, which is why we distribute the negative 1. So then we get 2x cubed plus 3. Now I'm going to multiply negative 1 and x squared. So that's minus x squared. Negative 1 times negative 4 is positive 4. So I'm going to add a positive 4. So when we subtract polynomials, we have to be careful. The tendency sometimes with students, the biggest mistake I see is that they subtract x squared, and then in this case, they would subtract 4, forgetting that they have to distribute the negative. Now let's look at like terms. There's only one cubed term. There's only one squared term, but then we have 3 plus 4 is 7. And that's it. Let's do another quick example. Something a little more complicated. I'm mixing variables too. It's easy to use x and y's, but you should be comfortable with any sort of number. So I'm going to use w as a variable here. So the first thing we want to do is distribute the negative sign, or the negative 1, throughout the second polynomial in order to keep track of the idea that we're subtracting each term. So we distribute the negative 1. We distribute the each term. So negative 1 times 3w, that becomes negative 3w squared. Negative 1 times negative 6w becomes positive 6w, because negative and negative is a positive. Negative 1 times positive 3 becomes a negative 3. So when you become more comfortable, you obviously don't have to do these steps where you distribute. If you can just keep track of what you're doing, you can do the distribution in your head. But again, it's one of the most common mistakes I see from students is forgetting to distribute that to all terms. Now we're going to combine like terms. And again, this is not something you necessarily have to write out. I always recommend it when you're starting a college algebra course or intermediate algebra or any developmental algebra course. It helps you, it becomes a habit, and you're far more successful when you have a process, an algorithm that you can rely on, especially when you have quizzes, exams, where you are nervous, where you are a little bit unsure. It helps to have a process. It becomes automatic. So we combine like terms, and we get 3w squared plus 30w minus 3. Okay, so subtracting and adding is exactly the same. We need like terms. We perform the operation. With subtraction, the difference is you must distribute that negative to each term of the polynomial you're subtracting. Let's look at multiplying polynomials. And there's a few different ways we're going to look at multiplying. Multiplying can be the most confusing of the operations. So here we're multiplying polynomials. So an example, and again, it's good to start with an example. There's not much in terms of hard rules or definitions here. When we multiply, so we can multiply any terms in a polynomial. They don't have to be like terms to multiply. We can multiply 2x by x squared, even though they're different powers. So what we're going to do is distribute the 2x throughout the polynomial x squared plus 3x minus 17. We talked a little bit in a previous lecture about the distribution property. It's in the properties of real numbers. You should review that if this is a familiar thing to you. But I'm going to write it out literally. So I'm multiplying 2x by each term. So I'm going to do that first by just writing it. And then I'll perform the operation. So I have 2x times x squared. And remember, your exponent rules says that if I have two variables being multiplied, then I'm going to add the exponents. So this is 1 plus 2 becomes 3. 2 times 2x times 3x is 6x. We have a 1 here and 1 here. 1 plus 1 is 2. Then we have 2x times negative 17. So 2 times negative 17 is minus 34, and we just keep the x. So that's how we multiply a monomial, that's a one-term polynomial, by a trinomial, which is a three-term polynomial. We distribute the 2x over the second polynomial's each terms. All right, so what if we don't have a monomial? What if we have a binomial? So let's look at that. 2x minus 1, and let's say we have 3x squared plus 9x minus 1. So this is a little different. We're going to distribute again. We're going to use a distribution property. But we're going to distribute each term of this polynomial to each term of the second polynomial. And we're going to do this in steps. So we're going to distribute 2x. Then we're going to distribute negative 1. So in other words, I'm going to distribute 2x to each term in this polynomial. Let's write that literally. Let me write an equal sign here. So that's 2x times 3x squared. I'm just going to put pluses between them. We'll work out the signs once we do the operation. 2x times 9x plus 2x times -1. So that's the distribution of 2x throughout that poly. Now we're going to do the same thing with -1. We're going to distribute to each term in the polynomial. And I'm just going to have a long chain of addition here. So it becomes -1 times 3x squared plus -1 times 9x. That looks like an A. Plus -1 times -1. So now we're going to do the operation. So 2 times 3 is 6, x cubed plus 18x squared, -2x, -3x squared, minus 9x plus 1. Now we combine like terms, because now we are adding. We are through multiplying, so now we add. So we have a 6x cubed. Here we have 2x squared terms, so I'll put those together. We have 2x terms. I'll put those together, and then we have one constant. So 6x is by itself. And we have 18 minus 3, so that's positive 15x squared. -2 minus 9 is the same as -11, x plus 1. Okay, so that's how we combine or multiply two polynomials. So we had a monomial and a binomial. Anytime you have, however long your polynomials are, you're going to distribute each term throughout the second polynomial. So if I have a 4-term polynomial multiplied by a 4-term polynomial, I have to distribute each term throughout the second polynomial, which can be ugly, but that's how you do it. In the college algebra course, you're going to learn detached coefficients and some other techniques in which you can multiply polynomials a little bit more quickly. But until that time, that's what you do, distribution. Now, there's one caveat here, and it's sort of a special way to multiply what we're going to call binomials using a mnemonic FOIL. So if you're familiar with FOIL, this will be review. If you're not, FOIL stands for, each letter has a meaning. And this tells us in what way in order that we multiply terms of two binomials. Now, binomial is a 2-term poly, so a plus b is a binomial. X squared plus y is a binomial. So the way we do this is F stands for first. So we multiply the first terms in the binomial. That would be this times this, first terms. O stands for outside, or sometimes I hear outer. Multiply the outer terms. I don't know if there's 2 T's in outer. In other words, the outer terms are A and Y here. That's why I like outside. Outer sounds odd to me, but I is inside or inner. I'm pretty sure there's 2 N's in inner. And last for L. So the inside terms are this and this. The outside terms are B and Y. So that's what FOIL means. Anytime you hear FOIL, think first, outer, inner, last. First outside, inside last. So let's look at an example. And this is a form of distribution. So we are still distributing distribution, but we're going to call it FOIL here. So we have 2x plus 3 times 3x minus 18. But what I'm going to do is use the mnemonic f. So that means I take the first term, 2x, of the first polynomial or first binomial, and I multiply it by the first term of the second binomial. Outside terms. So the outside means that if I have it set up like this, the outside is 2x and negative 18. It's always the outside, however you've written it. If you swap these, you'll notice that the outside term changes, but that means the inside term also changes. So the inside terms are what's together, 3 and 3x. And finally, the last term is this and this. So 3 and negative 18. In binomials, this is usually your constant term. So let's do this operation. 2x times 3x is 6x squared. 2 times negative 18 is negative 36x. Inside is 9x. The last term is 18 times negative 3, which is negative 54. So let's put those together here, and we're going to just put an addition. Now we'll keep the sign of the term. So negative 36 plus 9x minus 54. So since 36 is negative, I'm just going to write it subtract, and same with 54. Now we combine like terms. And the way this always works for FOIL is the outside and inside terms will always be like terms. The F and the L will always be single terms. There'll be nothing that we can combine. So you're always going to be adding and subtracting the inside outside terms. So negative 36 plus 9 is a negative 27x, and then the 54 stays out. So that's FOIL. Let's do another example here. Again, we're going to FOIL. It's just a different look, a little more complicated. Just to let you know that they don't have to have a particular look to them. They could be something like this. Now, when we get to the factoring preliminaries, you'll see that there's a way we could factor this first and then multiply, but let's just multiply this. We're going to use FOIL. You don't have to use this technique. You could do it just by combining the terms FOIL in a straight addition subtraction. But just for illustration, I think it's good to use this for now. I'm multiplying the first term of the first polynomial and the first term of the second polynomial. So let's just do the operation. 14 times 2 is 28. Now x squared times x squared is the same base as x, so then we add the exponents. 2 plus 2 is 4. The outside terms is 14x squared times negative 3x. So that is 12, 3, 48, no, 42, negative 42. And x, 2 plus 1 is 3. The inside is 4x times 2x squared. So that's 8x cubed. And then the last terms are 4x minus 3x, which is 12x squared negative. So let's put this all together. We have 28x to the fourth minus 42x cubed plus 8x cubed minus 12x squared. And again, you can see how the inside-outside terms are the only one that are like. So we're going to take negative 42 and add 8, or 8 minus 42, which will give us negative 34, x cubed minus 12x squared. So that's it. And again, if we wanted to simplify it, we could factor some stuff out of this. So look for the factorization lecture coming up. All right, so that's FOIL. Now there's some nice forms. We'll call these shortcuts. The first one we're going to talk about is called the difference of squares. If you forget the difference of squares, you can always FOIL. But the definition of the difference of squares is if I have a plus b times a minus b, this will always be a squared minus b squared. So if I see something where the a and the b are just the differences, addition and subtraction, I can just automatically write it as the square of a minus the square of b. So why is this true? Well, if we FOIL this, first terms is a times a is a squared. The outside terms is a times b. So that's negative b. So this becomes a subtraction. The inside terms is a times b. And since these are real numbers, they commute. So I can write them in this order. Instead of b times a, I can write it as a times b. And then last we have b times b is b squared, and that's a negative. And you'll notice these two terms cancel. So that's a squared minus b squared. So again, this is just a shortcut. If you forget, you can distribute and get to the same conclusion. Let's look at an example. X minus 1, x plus 1. So the rule says if I have something that looks like this, really simply, I could just take the first term and square it and subtract it from the second term squared. In other words, x squared minus 1. So that's the multiplication. X minus 1 times x plus 1 is this x squared minus 1. And if you forget, again, FOIL, and you'll get to the same answer. How about 2x plus 7, 2x minus 7? Well, I have the difference of squares. So that means I could take the first term, square it, and subtract it from the second term squared. Well, you notice that's minus the quantity of 7 squared, not plus negative 7. So we're not squaring a negative. So that becomes 4x squared minus 49. So that's a short way to do FOIL. If you recognize, you in the factorization lecture coming up, we'll be undoing these, and there'll be some ways to shortcut some factorizations when we have special forms. All right, so lastly, we want to look at polynomials with several variables. So in college algebra, you're not just going to be working with x's, you'll be working with xy's. That's 2 dimensions, sometimes xyz, 3 dimensions. So we could have multiple variables in a polynomial. And then what do we do? How do we handle that? Well, the rules are exactly the same. Example is 3x minus 1 times 2x plus 7y minus 9. So you notice here we have a y and an x. So we're going to use the distribution that we learned. We're going to distribute the 3x to each term, and then we're going to distribute the negative 1 to each term. And we're going to write that as a long string of addition. So 3x times 2x. We're going to add that to 3x times 7y. And we're going to add that to 3x times -9. So that ends the 3x distribution. Now we're going to distribute -1. So -1 times 2x plus -1 times 7y plus -1 times -9. All right, so that's the distribution. We distributed 3x and distributed -1. Now let's perform the operation. So 3x times 2x, remember we can multiply any term together we want. There's no restriction there. That becomes 6x squared. 3x times 7y. We can multiply the 3 and the y. That becomes 21. Now, I can't combine x and y like I would if it was 3x times 7x. That would be 21x squared. So instead, we just write it as the product x times y, because that's what's happening. So we don't write that any other way. If there was y squared or another combination of terms, we can look at in another example and see what we get. But you're going to write them as a product and combine like terms. I'm sorry, and if they have the same base, add the exponents. But otherwise, you're just holding on to the variable. And finally, 9. All right, so we have 6x squared plus 21xy minus 7x minus 2x minus 7y plus 9. So the only two things that are like are this x's here. So we're going to combine those because they are like terms. So that's negative 29x minus 7y plus 9. So we cannot combine any other of these terms. So we are done. All right, one more example. Let's use some other variables here. I'll use a and b. Typically, we don't use a and b as variable, but again, it's just so we get more comfortable with looking at different variable letters. So I'm going to distribute here b squared over each term. And I'll write that literally. Again, if you get good at this, you could just do this in your head. But till that time, be careful, because it's easy to forget terms, skip terms, miss signs. All right, now we're going to distribute -1 through each of the terms. So -1 times a squared plus -1 times 2ab plus -1 times b squared. Often find that college algebra students try to minimize how much they have to write. This is a bad strategy. You should always write as much as you can until you're comfortable with the operations, right? Until you've created an algorithm, so to speak, a process by which you do these things. Only then should you shortcut yourself here. All right, b squared times 2ab becomes 2ab. Now, b is the same base, so I'm adding 2 and 1. This becomes a cubed. This becomes b to the 4th minus 2a squared minus 2ab minus b squared. From a previous lecture on exponents, we can write a squared b squared as ab squared plus 2ab cubed plus b to the 4th minus 2a squared minus 2ab minus b squared. So are there like terms in here? Can we add any of this stuff? It turns out no. this is it. This is a multiplication of polynomial. We cannot add it. So this is it. All right, that's all I wanted to talk about today. We'll say end. Now next time, the next lecture will be about factoring polynomials. Multiplying polynomials one direction, factoring polynomials is sort of undoing a distribution, undoing a FOIL. It's going the opposite direction. So the next time we will look at that. This ends this lecture. Please like and subscribe. It helps us out. Comment if you can. And I hope you have a great day. Hello. We are continuing with our college algebra lectures. This is lecture 6. We are still in the prerequisite section. So this is mostly just a review for college algebra. So you can use this as a primer if you are taking a college algebra course. And this is probably maybe the most important of the sections that we're going to cover. Polynomials is pretty important, but factoring is very, very important. We'll be using it a lot during the course. So it's something you want to have a handle on. We are going to cover different kinds of factoring. The list here: greatest common factors, trinomial factor, factor by grouping, factor of perfect square trinomial, differences of squares, sum and difference of cubes, and then look at, lastly, factoring expressions where there's fractional or negative exponents, sometimes called rational exponents. So let's begin. The first thing we should look at is, what is factoring exactly? When we say we're factoring something, what do we mean? Well, let's think of a number. So consider the number 36. We can break 36 up into its prime factorization. So one way to do that is to make a tree. 36 is 6 times 6. 6 is 2 times 3. 2 times 3. So we can write 36 as 2 times 2 times 3 times 3. Of course, we can also write it as 2 squared, 3 squared. So this is the prime factorization of 36. It's the factors that make up 36. So there's an analogous correlation here to polynomials. We could factor polynomials the same way we'd factor numbers. Now, the notion of prime isn't something we have, but reducibility, and that will come more in the course. But for now, let's look at some technique to factoring, breaking up a polynomial into its factors. So let's look at the greatest common factor. The greatest common factor is the first thing you always want to look at when you're factoring a polynomial. You want to look at all the terms of the polynomial and see if they have anything in common. Now, if you need a review of polynomials, see lecture 5. I'll put a link to it here. So we're going to assume you understand what a polynomial is. So here's our first example: 2x squared plus 4x. That's a polynomial expression. Now we want to take out what they have in common. So what do they both have in common? So let's look at the coefficients first. We have 2 and 4. And we can see that 2 divides 2, 2 divides 4. So what they have in common is 2. Now, what about the variables? Well, the first term has an x squared, the second term has an x. So the greatest common factor for these two is x. So that means that what they have in common, the greatest common factor, we'll say GCF, is 2x. So I could take a 2x out of both of these terms. So what do we mean by that? What do we take out of? Well, it's essentially a division. If I have 2x squared and the greatest common factor here is 2x, I'm dividing this. And this leaves us with x. The same with 4x. I'm essentially dividing it by its greatest common factor, which leaves us with 2. So when we take out, so to speak, a 2x, we are left with x, and we're left with 2. And so that's the greatest common factor being pulled out of 2x. Now, is this correct? You can always check by multiplying back. So what I mean is you can distribute to see if you get the original expression. So 2x times x is 2x squared. 2x times 2 is 4x. And that was indeed our original. So this is a factorization of this binomial. If you need to review again of polynomials and multiplying, adding, subtracting polynomials, look at the previous lecture, lecture 5. Let's look at something a little more complex. We will run through a lot of examples in these lectures. There are rules, of course, and theorems and corollaries and lemmas, but examples of these terms, these definitions, these lemmas, corollaries, theorems are always valuable. So here is a polynomial expression, 30x cubed y minus 45x squared y squared plus 135x y cubed. So what we want to look at is what they have in common. So let's look at the coefficients first. We have 30, 45, and 135. We'll ignore the negative. We'll just keep it negative. Each of these is divisible by 15. So the greatest common divisor, but we're using factor, for the coefficients is 15. Now the first term has x cubed y, the second term has x squared y squared, and the third term has xy cubed. So the greatest common factor, let's look at these separately. Let's look at x's first and then y second. So the first term has 3 x's, right? X cubed is x times x times x, x squared is x times x, and the last one is just x. So that means they all have an x in common. Usually you're going to take the lowest power of variable. So here the lowest power is this 1, so we're going to take a 1 out. Because if we divide x by x cubed or x squared, we're going to get a negative exponent. So we want to make life easier, so we don't want negative exponents where possible. Now the same thing with y. We have a y here, y squared, y cubed. So the lowest power is 1, so we have xy. So that means our greatest common factor is 15xy. So we're going to take 15xy out of each term. I'm going to write that out here. So 30x cubed y. Let's do these really quick on the side, and we'll do each term as a division. So obviously 30 goes into 15 2 times, or 15 goes into 30 2 times. X cubed, x divided by x leaves an x squared, and y divided by y just leaves 1. Now negative 45x squared y squared divided by 15xy. will leave us with -3, because 45 divided by 15 is 3. Negative x squared divided by x leaves an x. Y squared divided by y leaves a y. And lastly, 135xy cubed divided by 15xy. Now, 135 divided by 15 is 9. X divided by x is 1. Y cubed divided by y is y squared. So 15xy taken out leaves with x squared minus 3xy plus 9y squared. And that's the factorization. Usually when we are left with the parentheses, we want to see if that's factorable. The inside, there's nothing left that we can take out GCD-wise or GCF-wise. We'll get into other techniques in this lecture. And then we ask the question, are we done when we are looking at an expression? We keep factoring until we can't factor anymore. And if you need a little bit of refresher on exponents, see our previous lecture on exponents. Again, I'm going to have to assume that you know some stuff. So let's move on to trinomial factoring. A trinomial is a three-term polynomial. It has three terms, usually of the form. Now we're going to do two different forms here. We're going to do the first one, we're going to do, say, x squared plus bx plus c, where b and c are just real numbers. And we're going to assume that there's a 1 in front of x squared. So this process is essentially reverse foiling. We foiled in the previous lecture is a form of multiplication, multiplying two binomials. Now we're going to look at how to undo a FOIL. In other words, how to factor a trinomial. So we want essentially x squared plus bx plus c to equal two binomials. And when the first term is x squared, we can assume that we have x and x in the first position. So the technique here is we have a little handy table. And the way we do this is we want to multiply two terms that will equal our c term, that when we add them, equal our middle term or b term. So we list the factors, and then we add them. We're going to have multiple lists of factors of c if c is not a prime number, and combinations of positive and negative depending. And then we're going to add those and then see if they equal b. When they equal b, we found our factorization. All right, so that's a lot. So let's look at an example. We have x squared minus 7x plus 6. So we want to factor this, and we want to use the technique we just looked at. So conceivably, we should be able to factor this into two binomials. And again, x squared is x times x. Now, to get the outside terms, what we're going to do is we need two numbers that multiply that equal 6. Then we add equal -7. So we can really just quickly list some factors. If for 6, it's not too hard. We need it to be positive. So 6 times 1, -6 times -1, 2 times 3, and -2 times -3. So those are the factors of 6. Now I'm going to add those. So in other words, I'm going to add 6 and 1. I'm going to add -6 and -1, 2 and 3, and -2 plus -3. So this is 7, -7, 5, -5. So we want it to equal -7. So that's our guy right here. So that means we put -6 and -1 in here. That's the factorization. Now, if we want to check it, we would FOIL. So we get x squared minus x minus 6x plus 6, which is x squared minus 7x plus 6. So that checks out. So that's the factorization of x squared minus 7x plus 6 is x minus 6, x minus 1. Two binomials. So that's handy, undoing FOIL, factoring. Let's look at a case when our leading coefficient from our leading term is not 1. So an example is 6x squared plus x minus 1. Now let's look at a form of a quadratic. Ax squared plus bx plus c, where a, b, and c are any real number. And the first thing we're going to do with this method is we're going to take out our a, b's, and c's. So a here is 6, b here is 1, c here is -1. So what we want to do first in this case is find factors of AC. So AC is 6 times -1, so -6. So we want factors of -6. Two, -3, -2, 3, 1, -6, and -1, 6. So we're going to sum these. So 2 plus -3 is -1. -2 plus 3 is 1. 1 plus -6 is -5. And -1 plus 6 is 5. Now, what do we want this to equal? Well, we want it to be equal to b, or in this case, equal to 1. So if we looked at the chart, it would be factors of AC that equal b. So multiplication and addition. So what we have here is -2 and 3. So what we do is we put an x to each of these terms. So -2x and 3x. And this technique, this grouping technique, is we're going to add them. And then we're going to have our 6x squared and our -1 out here. So we essentially broke up that middle. The middle was, remember, x. So we broke it up between -2x and 3x. And the reason we're going to do that is we're going to group them. Now I'm going to group the first two terms, and then the second two terms. And then we're going to factor the greatest common factor from each term. Not from the total, but from each term. So I'm going to look at what 6x squared and 2x have in common, and that's 2x. That leaves me with a 3x and 1. And then we have a 3x minus 1 over here. Now you can tell we did this in such a way that we are left with this two binomials that are exactly the same, and that's on purpose. So we're factoring out the GCF from the entire expression. So if we think of this as being in parentheses, the first term is 2x times 3x minus 1, and the second term, we can think of this as being 1 times 3x minus 1, if that's easier to conceive. So they both have 3x minus 1 in common. So I'm going to bring out a 3x minus 1, and I'm left with a 2x plus 1 afterward. So that's a factorization when we have a number in front of x squared that isn't 1. So let's write this down. So this is what was factoring trinomials by grouping. So we can write down the algorithm, and this will have the form ax squared plus bx plus c. So the first thing we did was we listed the factors of AC. Next, we found we'll call it P and Q, that are factors of AC. That add to B, or P plus Q is equal to B, and P times Q is equal to AC. So those two things have to be simultaneously true. The third thing we did was we factored the GCF of each term well, nope, I skipped a step, didn't I? The third one is where we have to group these. So we rewrite as ax squared plus px plus qx plus c. So in other words, the p we found in the previous step, we're going to add the x or multiply the x to it and then put it in the middle of our equation or our expression. And then we group and factor the greatest common factor from each term. Five, we factor the greatest common factor of the expression itself. So once we've done the GCF of each term, then we do the GCF of the expression. And that's how we handle where A is something other than 0, or 1 would say. A is always non-zero, but if A is not 1, then this is the method we can use, which isn't too bad. It allows us to factor rather quickly. Another method, when I learned this years ago, was what's called trial and error, which is essentially doing the same thing. In the case where we had 6, I learned to write all possible combinations of this. And you can see how this gets kind of unruly, and then just do a sort of guess of factors of the last term. So this is more of an algorithm that works every time. The guess and chug method is not great. So I suggest getting comfortable with that. Sometimes you can just see it. Most of the stuff, when you do it enough times, you will look at a polynomial and sort of suss out the factorization. All right, so next we're going to talk about factoring. Perfect square trinomials. And these have a particular form that allows us a sort of shortcut. So the methods that we just learned work on these. These are just sort of shortcuts that are really handy for a quick factorization. So I'm just going to write down the rules first. So these are the two rules. A squared plus 2ab plus b squared, we can factor to a plus b squared. And a squared minus 2ab plus b squared, we could factor to a minus b squared. Now, what does that mean? Well, again, it's determined by the polynomial look. And what do I mean by look? It's when you have a square, that's what I mean by perfect squares, of the first and last term. If I were to take those terms and square them, they would equal 25x squared and 4. In other words, is this perfect square? Well, I know I can write this 25x squared as 5x squared. And I can write 4 as 2 squared. So in our above form here, that means that we have a is equal to 5x and b is equal to 2. So all we really need check now is this is a positive. So we have to see that does 2ab equal 20x? If it does, then we have this form. We can use a plus b squared. So 2 times 5x, that's what a is, and b is 2, equals 10x times 2 equals 20x. So that means that this factorization is just 5x plus 2 squared, meaning it's a perfect square. 5x plus 2 squared is our factorization. Again, the middle part you can kind of see just from the fact that we have 5x times 2 times 2. You don't necessarily always need to write this down, but as you're learning, it's good. It's good to write. You can never write too much. I suppose you could write too much, but when you're starting, write out as much as you need to write out to feel comfortable. Now, if you're in a class and you're handing this in, maybe be more strategic about what you hand in, but most professors like to see work. I know I do. I also like to see how people think, so it helps to write out. So is this perfect? Well, we know we can write this as 7x squared, where a is going to be 7x. And 1, well, 1 we could always write as 1 squared. Kind of cheating, but that's how it is. So that's b is 1. Now, 7x times 1 is 7x times 2 is 14x. So yes, we can use this form because the middle term works. So that means we can take 7x and it's minus 1 squared. It's a factorization of 49x squared minus 14x plus 1. So that's a handy thing to do. You can, again, you can use the previous grouping factorization method to factor 49x squared minus 14x plus 1. It'll take you a bit longer, but it'll work. Let's look at something called factor the difference of squares. Ooh, keep hitting the erase button. And now I'm not. Okay. So again, this has a form. If I have a squared minus b squared, I can always factor this into a plus b, a minus b. So it becomes an identification problem again, where I just have to look to see if I have the necessary conditions met. So 9x squared minus 25. Now, do I have a square and a square? Well, this is equal to 3x squared. And 25 is equal to 5 squared. So yes, so a here is 3x, b here is 5. So I should be able to factor this between 3x minus 5 and 3x plus 5. And again, if you want to check, you can FOIL. FOIL will always tell you if you are correct because what you multiply back should equal the original polynomial. Next, let's look at something called the factoring of the sum and difference of cubes. The sum and difference of cubes is, again, a form much like we just went over, or a cubed plus b cubed. If we have this particular form, it tells us that we can factor this way. And if we have a squared minus, or a cubed minus b cubed, we can factor it this way. So you notice that in the top, we have an a plus b, and then a squared minus ab plus b squared. And the bottom, we have a minus b, a squared plus ab plus b squared. Something you should memorize if you're good at memorization. Otherwise, keep writing it down. It'll sort of stick. So let's look at an example. We have x cubed plus 343. So we just need to identify if the first and second terms here are indeed cubes, right? So obviously x cubed is a cube. So our a here is x. But what about b? Well, 343 is 7 cubed. So we'll say that b is 7. So that means that we can factor this by the first form. We can take a plus 7 times x squared minus 7x plus b squared is 49. Now, we would ask ourselves, can we factor x squared minus 7x plus 49? What we have right now, what we've just learned, no. We're going to say we're done. There's other ways we can look at that quadratic, but for now, let's just say we're good. All right, let's look at another example for the other form. 27y cubed minus 8. So again, this is an identification. Can we write 27y cubed as a cube? And there shouldn't be any shock that 3y to the 3 is that. And so that means that a is 3y. And we can write 8 as 2 cubed. So that means that b is 2. So we put it into our second form, which means that we have 3y minus 2 times, now we have 3y squared, right? So that's 9y squared plus ab. So ab is 6y. And then b squared, which is 4. Well, that's a factorization. Again, we would ask ourselves if 9y squared plus 6y plus 4 is factorized. We're going to say yes for now. We can always look at that a little bit later in the course. So now we are going to look at factoring expressions we'll say with rational or fractional exponents and or negative exponents. So what do we mean? Again, if you need to review, go back to lecture 5 or 3. Negative and fractional exponents look like this. So the video on exponents, you can learn how to handle these. All the rules are in those videos. So I'm going to assume you know that. So let's look at an example, 2x to the 1/4 plus 3x to the 3/4. So we can still factor this. Remember, x to the 1/4 is the same as saying the fourth root of x, and x to the 3/4 is the same as saying the fourth root of x cubed. We're not going to write it that way. It's much easier to look at it as fractional exponents. Now I want to use the same rule for these powers. I'm going to use the smallest power. So I know 1/4 is less than 3/4. So I'm going to think that the greatest common factor of the variables is 1/4. So what we'll do here is we'll divide each term by x to the 1/4 and see what we get. So remember that when I have a denominator, same base x, I just subtract the exponents. So this becomes 2x to the 0, which is 2. Now what about 3x to the 3/4 divided by 1/4? This becomes 3x to the 3/4 minus 1/4. What's 3x minus, or 3/4 minus 1/4 is 2/4 is 1/2. So this is equal to 3x to the 1/2. So it means the factorization is when we take out an x to the 1/4, what are we left with? We are left with 2 and a 3x to the 1/2. All right, let's do something a little more complex looking. The rules are the same. The exponents, the way we handle them are the same. So trust your rules. To write something ugly, 5x minus 1. This is a quantity to 3/4. We're going to add that to 7x times 5x to the negative 1 to the negative 1/4. And we want the 5x minus 1s to be the same base so that we can handle this exponent. So we want to factor from each term what they have in common. Now, what's the smallest power here? Well, negative 1/4 is smaller than 3/4. So let's say that we have the greatest common factor here is 5x minus 1 to the negative 1/4. So let's look at each term separately. And at some point, you are going to not do this step, this intermediate division step. Now, I'm not saying you're going to do it in your head, but you can basically just subtract the powers and get to the same spot. But I just want to illustrate what's happening. So when we divide that, we're doing 3/4 minus 1/4, which is the same as 3/4 plus 1/4, which is the same as 4/4, which is 1. So the first term leaves us with a 5x minus 1. 7x times 5x minus 1. Sometimes I just miss the button. The negative 1/4 divided by 5x minus 1 to the 1/4. This becomes 7x. This is negative. 5x minus 1 to the negative 1/4 minus 1/4, which is the same as negative 1/4 plus 1/4, which is 0. Anything raised to 0 is 1. So this means that we have 7x times 1, or just 7x. All right, so that means we factor out a 5x minus 1 to the negative 1/4. And what are we left with from the first term? 2 5x. Yep, I wrote 5 and I was thinking 2. So 2, 5x minus 1 plus 7x. Now that's the factorization. We could maybe make the inside prettier if we want. Why not? Distribute that, we get 10x minus 2 plus 7x. To make that even prettier, we have 5x minus 1, so negative 1/4. 10x plus 7x is 17x minus 2. So there's a factorization of that ugly polynomial. And in math, sometimes pretty stuff is better. Sometimes it doesn't matter. But that is generally a factoring strategy. We did some examples and some methods. But what you need to do with factoring, especially if you're new and just beginning, is to do a lot of them. Factor a lot of expressions, factor a lot. Use different techniques, explore which ones make more sense to you, whatever method you're using, and then check. Foil back, multiply, distribute, just to check to see if you are getting what you need to get. So that ends this lecture 6. Hopefully, I didn't go quickly and everything made sense. If it didn't, please leave a comment and I can address that. And the next lecture, lecture 7, will be on rational expressions. Rational expressions are, example would be 2x over y cubed plus x over z squared. Basically fractional polynomials. That's what we'll handle next in the continuation of this lecture series. And the next lecture will be the last lecture of the review section. And I think lecture 8 will be the beginning of the actual college algebra lectures. So hopefully you can be able to tune into those, and we'll see you next time. Like, subscribe, comment, do whatever. Appreciate it. Have a good night. Hello. This is the last of the review sections from chapter 1, which is a prerequisite chapter. Section 1.6, which is rational expressions. We'll look at simplifying, multiplying, dividing, adding, subtracting, and simplifying more complicated looking rational expressions. This is from the OpenStax College Algebra 2nd edition. You can find a download to that book in the description. It's open source and free. That's why I'm using it. I'm using it as a kind of guide to go through this college algebra lectures. So lectures 1 through 7, which you could find in the playlist, the college algebra lectures, are all review. So if you're going to a college algebra course and you want to look at some stuff that you need to know for college algebra, this is the lectures 1 through 7 will help you with that. It's a review. The next lecture will get into the actual beginning of the college algebra lecture, or college algebra course lecture. We are going to look today at rational expressions. What is a rational expression? That's where we're going to start. So what is a rational expression? We say the word rational. Not to be confused with rational numbers, but in the same context, it's a fraction. Rational we think of as a fraction. So it is like a rational number in that it can be expressed as a fraction, but where they differ is that a rational expression is essentially a polynomial fraction. Now it could have a polynomial on top and a polynomial on bottom. Now we think of constants as a polynomial if we think of it as being some number, say 2, where there's x to the 0, and say 3y squared. This is a rational expression. There's a polynomial on top and a polynomial on the bottom. So both numerator and denominator will have fractions. Students generally do not like fractions of any kind. So this is always a good review area for college algebra students. Even if you're in the course and you're doing well and you need some help with rational expressions, this would be a good video to look at. Our first example is x minus 6 and x squared minus 36. This is a rational expression. So the first thing we want to do is simplify rational expressions. So how would we simplify something like this? Well, the technique is to factor and cancel when possible. So review factoring if you haven't already and need a review. I will put the link to the lecture somewhere above or below down there. So we want to factor the top and bottom if possible, and then cancel what can be canceled, and that will be how we simplify this. So I'm going to look at this, and we have, I'm just going to write x minus 6. Now I need two binomials that multiply that give me x squared minus 36. We know that this is a perfect square. X squared and 36 are both x and 6. Again, in our review of the lecture on factoring, we'll give a technique of how to do that. So now we cancel. I see that there's a x minus 6 and an x minus 6. So this is equal to 1 over x plus 6. So that's simplification. If this is unclear, think of a fraction, something like this. Now I can break that up into its factorization. 4 I can write as 2 times 2, and 8 I can write as 2 times 2 times 2. So now I can cancel the like terms, and we're left with 1 over 2. The same will be true of rational expressions. We can cancel once we factor. So again, lecture 6 will be factoring review. Let's look at how to multiply rational expressions. As you can probably tell at this point, algebra, college level algebra, high school level algebra, all build upon each other. So we're using a lot of concepts we went through in lectures 1 through 6. This will be no different. When we multiply polynomials, we want to be sure that we know how to. So look at some of those review lectures. So let's say we have a expression we want to multiply it. So these are two expressions, x squared plus 11x plus 30 divided by x squared plus 5x plus 6 times x squared plus 7x plus 12 divided by x squared plus 8x plus 16. So we want to multiply this expression. Now we could just multiply it with the techniques that we learned in previous lectures, that we just distribute one term in, say, this term over the entire second polynomial and continually do that until each term has been distributed across the second polynomial, and do the same for the denominator. Now you can see that that would lead us to having 6 terms on top and 6 terms on bottom. No, 9 terms, sorry, 9 terms on top, 9 terms on bottom. So a good strategy here is to factor first. We factor the top and bottom of both of these expressions, we might be able to cancel stuff, and then we can multiply if we want. And when I say want, it's stylistic. So x squared plus 11x plus 30, we can factor two numbers that multiply that give me 30, that when I add them give me 11, which would be x plus 6, x plus 5. The denominator, two numbers that multiply that give me 6, that when I add them give me 5. That's x plus 2 and x plus 3. Put an equal sign. And then the x squared plus 7x plus 12, the same technique, two numbers that multiply that give me 12, that when I add them give me 7. 4 and 3 are good candidates. And x squared plus 8x plus 16. This is one of our forms from the factoring lecture, but you can see that we can factor this into x plus 4 times x plus 4. So if you're not convinced that this is the actual factorization, you could FOIL these back out and you'll get the original polynomials. So let's cancel. Let's first look at maybe a simple example using numbers of how you cancel stuff. So we had 2 times 2 and 2 times 2 times 2, which was 4 over 8. So let's say we have something like 2 over 5. Well, we cancel these guys. There isn't a 5 in the numerator of either expression, so I can cancel the 2 here with the 2 here, even though they're in different expressions, because it's being multiplied. So these two will cancel as well, and then this will become 1/5. Same thing applies here. If I have a term in the denominator of one expression and the same term in the numerator of the other expression, I can cancel. So that's why this x plus 3 cancels. X plus 4 will go away. And that's it. So multiplying through, these become 1, by the way, just in case you're wondering what happens. Well, those become 1. And then we have x plus 5, then x plus 2, and x plus 4. So at the beginning of the example, I said that if we can multiply out or not. I'll leave it in factored form. But if you FOIL these, you'll get a polynomial over polynomial. But leaving it in factor form is generally a good idea. No sense in making more work unless you're trying to solve or do something else. Leave in factor form. So that was multiplying rational expressions. What about dividing rational expressions? One question you might have is why do we start with multiplication and division and not do addition and subtraction? Addition and subtraction seem to be easy conceptually, but with polynomials, it's actually a little more difficult add and subtracting polynomials than it is to multiply and divide them. So that's why we start with the easier stuff. So if we need to do other things with the adding and subtracting, then we have a sort of a basis for multiplication and division. So we're looking at examples I could write out sort of an abstract rule for these, but I think it's best to look at examples. Examples help us sort of apply. If you look at these as being algorithmic in some way, that if you have different polynomials, that you could sort of go through the process and not have too much of a hard time. So what we have here is 1 over x squared divided by x plus 1 over x. If I wrote this as a fraction, meaning if I have 1/2 divided by 1/4, I can write that as a division of fractions. Most people don't like to do that, and there's a reason. It's ugly. So this guy is 1 over x squared divided by x plus 1 divided by x. So this is ugly. And honestly, it's more difficult to handle. So there's a rule. If I have, let's say, a over b divided by x divided by y, and so I'm dividing these two fractions, I can write these as reciprocal multiplication. So I take the reciprocal of x over y, which is y over x. It's basically flipping it upside down. I think in a previous lecture I spelled reciprocal wrong, and that's embarrassing, but made sure I spell it right this time. So with this polynomial expression, this rational expression, we're going to do the same thing. Instead of writing that ugly fraction on fraction, we have this becomes reciprocal multiplication. And so we can write division as multiplication. This just becomes, let's write it as a single fraction. So this is x squared, and this is x plus 1. Now, I have an x on top and an x squared on bottom. Essentially, that means that I can take, this is x1 minus 2. This is x negative 1. It's 1 over x. You don't need to do that little aside, but this is why it works. Again, review your exponent rules. I think that's lecture 3. So we can write this as x, well, x cancels, and then we have 1x on the bottom. So this is 1 over x times x plus 1. So that's the division of those expressions. We get something a little bit easier to handle. So most times in these examples, I try to do something that's a little clear and then something that maybe looks a little uglier. Just to give us sort of different looks. So here is a rational expression. So we can handle this one of two ways. We can factor first and then write this as a reciprocal multiplication, or we can write it as reciprocal multiplication and factor. Doesn't really matter which order you're going to do this. I am going to write it as a factorization first. Oops, I forgot this. All right, so I can write the numerator here. Again, the hard part seems to be in the factoring. So review that if you need. But here's how we factor. Divided by 3x to the 4th, x minus 2. This will be the AC method for the top, and the bottom I'm just using the what two numbers multiply give me 14. Then when I add them, give me positive 5. That would be x plus 7 and x minus 2. Okay, so that is the factorization. Now, let's write it as reciprocal multiplication. And remember, reciprocal is taking the second fraction, turning it upside down, and writing that as a multiplication. So the numerator becomes the denominator becomes the numerator. And then we have this. So again, the order in which you do this, there isn't order operations on reciprocal multiplication and factoring necessarily, so you can do whichever one you want first. I'm going to now cancel some stuff. You're going to see something amazing happen. So this ugly division is just equal to 1. Everything cancels means that everything that cancels is replaced with 1. So 1 times 1 times 1 times 1 and so on is just 1. So if you ever need a really ugly way to write 1, write this expression and you have a very ugly 1. Let's do another one that isn't 1. Let's use a different variable. Let's use y. So 3y squared minus 7y minus 6, 2y squared minus 3y minus 9 divided by y squared. Missing the button. Y squared plus y minus 2, 2y squared plus y minus 3. They're not necessarily looking at cases in these examples where something doesn't factor, because we want to get some examples where we know what to do with the factorization. We'll say that all 4 of these things were not factorable. Then the division would become reciprocal multiplication. Then we can distribute like we learned in the multiplying polynomials lecture. But that would just give us some ugly long polynomial. So you don't necessarily want to do that, but if you wanted or had to, you could. So I've chosen factorization, polynomials that factor, just so we can sort of see the process here. So I'm going to factor these first. This becomes 3y plus 2, y minus 5. And this becomes y minus 3. And this becomes y minus 1, y plus 2, 2y plus 3, 1. Now, what should be somewhat obvious is that if I am now in a division and I want to cancel, it's best to do the reciprocal first before you start canceling stuff. Because remember, the division is going to complicate the cancelization. It's not numerator and denominator. So writing it as a reciprocal has to come before the cancellation, unless the cancellation occurs on the same expression, meaning I can't cancel this and this if they were the same. I couldn't do that, not in division. So write the reciprocal multiplication first and then cancel. Of course, when you factor the right and left, you can always immediately start writing it as reciprocal multiplication to save yourself a minute. I'm writing it as an illustration so that if you want to rewind the video, you kind of see what came before what. So recip, roll call. I always want to say recip as RICOL, which is not right. So now I can cancel. I can cancel across numerators and denominators. What else we got? Y. All right. So y2. Well, this is a 3. Why did I write as at 5? My fault. So those cancel, those all become ones, and then we're left with 3y plus 2 and y plus 2. So my mistake here was writing this at 5. My chicken scratch sometimes confuses me. That should be a 3. This would be a 3. So those cancel. So the division leaves us with the expression 3y plus 2 divided by y plus 2. All right. So that's multiplying and dividing reciprocals, multiplying and dividing rational expressions. So now let's look at the more complicated adding and subtracting rational expressions. So let's remind ourselves that when we add fractions, say we have 1/2 plus 3/7, we don't just add the top and bottom. We need a common denominator. So to find a common denominator from 2 and 7, sometimes it's just easy to take the multiplication of 2 and 7. That's 14. So the common denominator will be 14. It's just a multiplication of the two denominators. And then I think about, what do I need to multiply the 1/2 by to get 14? Well, it's just the other denominator. And I'll write it like this. Now, what do I need to multiply 3/7 by to get a denominator of 14? Well, that's just 2. So doing the multiplication, 7 times 1 is 7, 14 plus 3 times 2 is 6, 7 times 2 is 14. Now this becomes a easier problem, right? Because we have a common denominator, which we write as 14, and then we add the numerator. So that becomes 13/14. So this is the exact same method we use for adding and subtracting polynomials. It's just harder and uglier. So let's do something simple first. So let's say we want to add this expression 4 divided by x, and we want to add it to 10 divided by y. So the common denominator here I'm just going to take the x and y and multiply them. So the common denominator will be x and y, x times y. So what do I need to multiply the first fraction by so I get an xy in the bottom? Well, I have to multiply top and bottom by y. And what do I need to multiply 10y by to get xy in the denominator? Well, again, that's going to be x over x. A legitimate question is, how can we multiply what this by y's and x's? Doesn't that change it? Well, remember that y divided by y is 1. And multiplying anything by 1, it just leaves itself. This is identity, right? This is from, I think, lecture 1 or 2. Everything has identity. So this becomes 4y divided by xy. Y times x is the same as x times y by commutativity. This is 10x over xy. So I can write this as a single denominator in a addition of the numerator. Now we can't add 4y and 10x because they are not like terms. And so that is the expression. So once we add, we get that. And we're done. So that wasn't too bad. These get progressively worse, unfortunately. Let's mix a variable in here. So let's say we have y plus 3 divided by y minus 2. And let's say we want to add that to y minus 3 over y plus 1. So what we've been doing essentially is taking in the previous example, that was a common denominator, but it's also the least common denominator, meaning I'm not having extraneous terms in there. So the lowest common denominator, or least common denominator, in this case will also be the multiplication of y minus 2 and y plus 1. Just like our xy case, just like in the 1/2 3/7 case, we're just multiplying the denominators. This will always work. It's advantageous to find the least common because it will save you canceling in the result, but canceling is much easier, I think, than fussing around with the common denominators. But that's a choice, I suppose. So I need to multiply this fraction by y plus 1, top and bottom, to get the common denominator. And I'm putting parentheses around just so that we don't get confused. And then this guy needs a y minus 2 over y minus 2. So this becomes on top y plus 1 times y plus 3 plus y minus 3, y minus 2, all divided by the common denominator, which we said was going to be, I'll put it in this order, y plus 1, y minus 2. Let me scroll up a little. So let's multiply out the numerator just to see if there's things that cancel, if it's possible to refactor once we've multiplied. Let me put that down here. So I'm going to FOIL this, which gives us y squared plus 4y plus 3. We're going to add that to this, which is 4, or y squared, sorry, plus minus 5y plus 6. That's divided by y plus 1, y minus 2. Combine like terms, we have 2x squared, so write that as 2y squared. We have a y term and a y term, so 4 minus 5 becomes negative y. And then 3 plus 6 is 9. And then we're going to leave that over here. So does 2 squared minus y plus 9 factor? Nope. So we leave it at that. You could also leave it here. I think the multiplication and combining like terms makes it look a little bit better. But again, it's depending on what you need to do once you've added these two things. In a calculus class, might be more advantageous to leave things in factored form. Most people that take college algebra are doing it for some prereq for some other major. But if you're a math major or a STEM field and you need to take calculus, the college algebra course is essentially a toolbox for calculus. It allows you to do a lot of things a lot easier in calculus class. So that's multiplication, division, addition, and subtraction. The subtraction will work the same way. Now let's mix stuff up. Let's write it out first. Simplifying. The text I'm looking at uses the word complex, which doesn't mean complex in the sense of a plus bi. That's a complex number. It doesn't mean that. So simplifying complex expressions, what they mean is hard or ugly or difficult. That's what they mean. So don't confuse complex here with complex. Simplifying complex rational expressions means we're just going to look at expressions that are hard or appear hard, appear ugly. And to get us off on the ugly bat here, that made little sense. But I think you get what I meant. Y minus x, or sorry, x divided by y minus y divided by x divided by y. So there's a number of ways to start. I'm sure as a viewer of this video, you'd be like, why didn't you do this? It's going to be quicker and much easier. I like to add steps and make sure that the viewer, the student, the interested party can follow through and see what's happening. So I usually take the long way around. That's fine. But again, there's always a quicker way to do these things sometimes, but these steps are guaranteed to work. So what I'm going to do here is I'm going to add the top, right? So we have a subtraction. So I'm going to do the same thing where I have x and y as denominators. So I'm going to multiply the first term by y over y. Oh, no, x over x. Subtract that from y over x, and I need to multiply this by y over y. Now the common denominators are xy, so I'm going to write that as xy, and then we have xx, which is x squared, minus yy, which is y squared, divided by y. Not too bad. Still ugly. Remember, this is a division. This is x squared minus y squared divided by xy divided by y. So we can write this as a reciprocal multiplication where we have x squared minus y squared divided by xy times 1 over y. And now we just multiply the tops and the bottom. So x squared minus y squared times 1 is just x squared minus y squared. And the denominator is xy times y, which gives us xy squared. So this expression that we started with doesn't look that much better, but at least we don't have fraction, addition, subtraction on top, and then divided by some other variable. We have a single rational expression, which is a little bit easier. But yeah, so ugly. Let's do another ugly one. Three divided by x plus 1 plus 2 divided by x minus 1 divided by x minus 1, x plus 1. Pretty ugly, but same process. We're going to add the top. The least common denominator, if we're adding the top, is x plus 1, x minus 1. So let's just look at the top here. And then we'll add the denominator after. So to get the common here, I need to multiply the left fraction by x minus 1 times 3 over x plus 1 plus 2x minus 1. So the right-hand side, I need to multiply the top and bottom by x plus 1, x plus 1. So this becomes 3x minus 1 plus 2x plus 1 divided by x minus 1, x plus 1. Again, there's an easy sort of way to think about this, to do the top and the bottom of this initial fraction, the larger fraction, and handle it all at once. But I'm doing this step by step so you get a better sense of what's happening. Now I'm going to look at the top here and see, do we want to simplify that? Well, let's not. Let's leave it as 3 times x minus 1 plus 2 times x plus 1, and then put this all under, or above rather, the x minus 1, x plus 1. And the reason we're doing that is because I see I have a lot of x plus 1s and x minus 1s here. So it's possible that there's some stuff that's going to cancel. So let's write this as reciprocal multiplication. That's x plus, well, should be x minus 1 plus 2 x plus 1 divided by x minus 1, x plus 1. So instead of dividing it by x minus 1 over x plus 1, we're going to flip it over. So this becomes x plus 1, x minus 1. Now this cancels. Now you would be tempted to cancel the x minus 1 with the x minus 1 on top, but remember that's an addition. So let's leave that alone. We have x minus 1 plus 2x plus 1 divided by x minus 1 squared. So now let's look at the top and see if we can reduce any. So we'll distribute the 3. We get 3x minus 3 plus 2x plus 2 over x plus, nope, x minus 1 squared. So that's 5x minus 1 over x minus 1 squared. There is no other simplification here, so that's the final answer. So we took this really nasty looking expression and we made it into something a little more manageable. Now, I'm going to write down a really ugly looking thing. So x squared plus 7x plus 12 divided by x squared plus x minus 6. We'll say we'll divide that by 3x squared plus 19x minus 28 divided by 8x squared minus 4x minus 24. And we'll divide that by 2x squared plus x minus 3 divided by 3x squared plus 4x minus 7. That's an incredibly complicated looking thing, right? If I have 1 over x divided by 1 over y divided by 1 over z, what does that really look like? Well, 1 over x divided by 1 over y divided by 1 over z is a really ugly way to think about it. We're not going to do that, obviously, but you can see how if I wrote it that way, this would be a little bit unruly. So let's factor and see if we can cancel stuff in the expressions themselves before we do anything else. So that's a good strategy, right? We're going to look at each expression separately. So we can factor this between x plus 4 and then x plus 3 divided by x plus 3, x minus 2. Then we're going to do this guy, 3x plus 7, x plus 4. Two-step factorization. There's a like term here. It's 4. If I take 4 out, I'm left with 2x squared minus x minus 6. So that would leave us with 4 times 2x plus 3, x minus 2. So again, do your factorization review. We have a video on factoring, which would be a good resource. Let's factor these. 3, x minus 1, and then 3x plus 7, x minus 1. All right, so that is a little bit better because we see in the expressions themselves, we can cancel some stuff. These x minus 1s go away. So that will leave us with x plus 4 divided by x minus 2 divided by nothing canceled in this. So this ugly guy is going to stay complete. And this guy simplified a little bit too. Okay. So recall your order operations, lecture 1. I'm going to multiply and divide left to right. So let's do reciprocal multiplication on the left side. So we're going to do 4. I don't want to write that in different order. So we have 4, 2x plus 3, x minus 2, divided by 3x plus 7, x plus 4. That's still being divided by 2x plus 3, 3x plus 7. So now I have reciprocal multiplication in the brackets here. So now I can cancel stuff. So this goes. This goes. And what we are left with then is 4, 2x plus 3 divided by 3x plus 7. Now let's write this as reciprocal multiplication. So 3x plus 7 on top, 2x plus 3 on the bottom. And then we notice that we have this nice cancellation. So this is actually just 4. So this ugly expression that we started with, where was it? Right here, is just 4. So if ever you want to write 4 in a really ugly way, you can write it this way. Okay, so that's it. That's all I wanted to cover. So let's say end. So the OpenStax text has the review. This chapter 1. This ends those chapters or those sections. So we are done. We will begin the actual heart of the college algebra course in chapter 2. And we will start with equations and inequalities. So chapter, my pen is dying, I think. Chapter 2 will be equations and inequalities. I think the first section is on the Cartesian coordinate system or the rectangular coordinate system, the xy's. So that would be the first place we start. So I hope this review has been helpful. And I look forward to seeing you in the next lecture. It will be lecture 8. So like and subscribe if you can. Thanks for watching, and I hope you have a great night.